Hello and welcome to HSS 405, Artificial Intelligence and Autonomy. This is the third of my agency lecture videos. It's part 2 because we started on part 0. Remember, the point of these videos is to review the 2,500-year history of philosophy and philosophical discussions on agency and autonomy. We're hoping to sort of provide some scaffolding to think about certain popular debates and the historical context in which they arise. And our goal in this class is to use this sort of scaffolding to approach two really important philosophical issues, the debate over free will and some contemporary debates over AI and robotics. So if you watched the first video, you were introduced to this table. In the previous video, I talked a lot about Aristotle's view of what it means to be alive, his view of the soul. In this video, I'm going to talk about the scientific revolution and what it means to be a machine, and in particular, how the scientific revolution rejects Aristotelian views. I'm not going to talk too much about Descartes today in this video. I'll talk a little bit more about Descartes and Kant in the next video when I talk about consciousness and the philosophy of mind. But our goal in this video is to talk about the scientific revolution, how it rejects Aristotle, and how it proposes a new mechanical framework, the Newtonian or classical mechanics, that looks at the world in a very different way from Aristotle, in this sort of reductive, deterministic way. And we'll see today how the classical scientific view interacts with and the discourse with the Aristotelian picture, especially over questions like, can life be explained mechanically? I also want to use this video to introduce a third, maybe an alternative to Newtonian mechanics, so-called complex systems theory. The idea is that complex systems theory is non-reductive, and so it can deal with complex systems in where there are sort of emergent organizational properties that arise. And so that emergent complexity, sort of systems theory, is the right framework for thinking about how life is a mechanical process. And in order to motivate this picture, I have a demo of the game of life, Conway's game of life, that I'll go through at the end of the video. Okay, let me get my head out of the way here a little bit. Okay, so here's maybe a little more technical introduction to this lecture series. We've already talked about the Aristotelian view, which I'm going to call teleological essentialism. This Aristotelian view that things have an essence and that they work to realize their telos, or their purpose. This is what I'm associating with the ancient worldview. And then, again, I'm introducing two sort of mechanical theories today. One is the classical or Newtonian mechanical view that thinks about things in terms of universal laws and fundamental parts that those laws operate on. And then at the end of the video, I'll introduce sort of systems theoretic view with feedback loops and organizing structure that's non-reductive. And I have a couple of slides for each of these. This is the first one. This is the Aristotelian view. And I'm not going to go through the entire Aristotelian framework again, but this is the sort of upshot, big picture view of Aristotle's metaphysics. Right? Remember, Aristotle has the 4 causes. There's the material cause, the stuff that it's made of. There's the formal cause, which is the structure or the principle on which it's built. And then there's the efficient cause, which is how the thing develops over time, or the process that the thing undergoes over time. And then there's the final cause, the end or the goal. So the typical example for Aristotle is using the acorn and the oak tree. Right? So the acorn is made of some stuff, but it has within it this essence, the essence of an oak tree. And this essence is an animating principle. It's what guides the development of the acorn over time. Right? So the acorn has this formal principle, has this essence of an oak tree, and because of that essence, it has an idealized end. It has a telos, a goal that it's after. The acorn, you might think, in some sense, wants to become an oak tree. Now, not every acorn will become an oak tree. Some acorns get enough water and sunlight and so on to grow into a big oak. I don't know if that's an oak tree, but imagine it is. The acorn grows into an oak tree. Not every acorn gets the chance to grow into an oak tree, though. Some acorns get eaten by squirrels. Some acorns freeze in the winter and never get a chance to develop. But right, so the telos here is not a fatalistic end. It's not predetermined that the acorn will become an oak tree. Instead, there's sort of these various options that might happen to the acorn, some of which result in the oak tree and some of which don't. But it's in some sense the principle within the acorn that it has the potential to become an oak tree, right? So Aristotle associates the matter with potential, and then the formal principle with the actuality, with what it wants to become, or its idealized end state. The acorn actualizes its potential by becoming the oak tree, and that final state, it's the formal animating principle in the acorn that moves it to become the oak tree. And that final state itself is the telos, the final cause, the fourth of the causes, and it's really the telos that structures everything else, right? The telos, what's good for the thing, tells you what it can be made of. This is more clear when we're talking about artifacts. If we know what it's for, then we know what it should be made of, the structure it should take, and maybe even how to build it. But remember, Aristotle thinks that this is not just the rule for artifacts and sort of human-designed objects, but this is the rule for all natural objects, that all natural objects have a material and a formal cause, but they also have a final cause. They also have a purpose and a goal. Importantly for Aristotle, each different kind of thing has its own different kind of motion and change. So the way that acorns develop into oak trees is just a different principle. It's a different sort of formal kind from the way that a child grows up into an adult human. We're different kinds of things, and so we have different formal principles describing our motion. Aristotle thinks that plants have a soul; they have a nutritive soul. So there's in some sense, there's the same animating principle. The same animating principle that's in the acorn is also in us. We're also nutritive. We also need nutrition to grow and develop, and so on. But we also have these other animating features. We're sensitive, and we're also rational. And this means that the way we move and the way we change is just different from the way that the acorn moves and changes. So Aristotle says that there's many kinds of motion and change as there are kinds of being. Right? You need to, in order to understand a thing, you need to understand the kind of thing that it is, and that will tell you how it moves, how it develops, what its end state is. Okay, and Aristotle thinks this works for the entire natural world. I'm still in the way here. Let me get myself out of the way. Oops. Good. So that was a big picture review of Aristotle. If you're still curious about some of those things, maybe go back and watch the first video or the video before this, and maybe also read some of the articles in the reading list. I don't want to get too much more into the details of Aristotle, but what I do want to do is talk about what's good and what's bad in Aristotle. So Aristotle has this view of agency or of life, where what it means to be what it means to be an agent in the sense of an animate creature, what it means to be alive, in other words, is that animate creatures have the kind of soul that allows them to move on the basis of internal drives, like sensations felt, and not merely the result of their natural motion. Remember, Aristotle has this view that the world is made of elements, and the elements have a natural place, that the earth is at the bottom, and then water on top of earth, and then air on top of water, and then fire on top of the rest of the elements. And so when things move according to their elemental structure, this is, for Aristotle, the natural motion. It's the motion that's inherent to that nature. But animate creatures like us also have a kind of motion that's not merely the elemental motion, but it's the motion of our teleological structure that the acorn develops in the oak tree. So this is a different kind of motion associated with the kind of thing that it is. So the reason that there are living creatures is because they have a soul, they have a certain kind of motion that's different from the inanimate creatures. Okay, so there's things to like about this view. There's things to maybe admire about the view. In a very general sense, Aristotle is concerned with the natural world. He's concerned with explaining the world around him. He's also concerned with practical activity. Unlike Plato, who's interested in these sort of high-minded abstract ideals, Aristotle is very much interested in how should we live our lives? How should we build a city? How should we act in order to live a good life? And these seem like very, very practical concerns, very, very much concerned with everyday life and the things we have to do to get along in an everyday sort of way. So this is, I think, promising. Another thing that I like about Aristotle, maybe you don't like this, but it's something that I appreciate, is that Aristotle has put in the work to develop a systematic and comprehensive view that's supposed to explain things from top to bottom. But this is not dogma. Aristotle doesn't think that this worldview has been handed to us by God or by the creator or anything like that. Aristotle arrives at his conclusions. He arrives at his worldview through a process of reasoning, and he explains this reasoning in his writings. He recognizes that his reasons are open to debate and criticism, and he engages those criticisms in order to revise and refine his views. Moreover, after Aristotle dies, these views are the subject of much scholarly debate and criticism and improvement over millennia. And again, this is not a dogmatic view. It's not a religious view in the sense that anyone thinks that it's divinely inspired. This is a view of human beings trying to explain their world, and it's one that humans have been engaging for over 1,000 years, 2,000 years. So this is all positive reasons to be encouraged by the view. There's also a picture of what we would today call functional organization in Aristotle that I think is very close to how we think about functional organization today, with a couple of important caveats. So these are good things, and I want to talk a little bit more about the functional organization. But there are also, of course, bad things. We mentioned some of these bad things last time, and just to sort of summarize, Aristotle makes a bunch of mistakes, just sort of brute factual errors, but also systematic confusions about how things work. Things like spontaneous generation and so on are just mistakes that if he was careful about his observations, maybe he wouldn't have made. Part of these mistakes are the result of serious theoretical and conceptual failures that maybe we can't blame Aristotle for having these failures 2,000 years ago. He did the best he could with them. And in fact, he was able to create this really impressive philosophical system despite these failures, right? So he was wrong in interesting ways. But there are two particular ways that he was wrong that I want to talk about in some detail in this video, which is, again, this idea of natural motion, and then which is how the physical world works. And then also this notion of teleology, purpose, that things have a purpose or an end or a telos, an idealized state that they aim to actualize. So I want to call both of these into question. We also talked last time in a little bit of detail about how Aristotle's views provide a kind of theoretical justification for systemic racism and misogyny, for sexism, and Aristotle says a bunch of bad things about women. He says troubling things about slavery, and these are all serious problems that need to be engaged and taken seriously. So we talked about this a little bit in the last video. There's a lot of material in the readings to engage these views. I don't want to press too hard on this right now because we will see that the sexism and racism is not unique to the ancient views, but in fact is to some extent embraced strongly by the scientific views that we're going to introduce in this class. And we'll see how this plays out with some of the political and social issues, especially in the next video. So the hostility to gender identity issues that we sometimes see today in the popular discourse, the commitment to a gender binary of men and women as being opposite and the only two possible genders. This is something that we see the roots for in Aristotle 2,000 years ago, and obviously we're dealing with these same sort of prejudices and theoretical biases and confusions today. But again, I want to sort of put a pin in the sexism and racism stuff and come back to this because this is also going to be a criticism for modern science. And what I want to do in this video is really just talk about the science, the sort of hard science today. So I want to talk about physics. I want to talk a little bit about biology. But let me go ahead and jump back quickly to talking about functional organization, the one good thing here in Aristotle. Let me get my head out of the way one more time. Oops. So remember from Aristotle's De Anima, he says, if the eye were an animal, sight would be its soul. So when Aristotle's talking about the soul, he's not talking about some ghost inside you, some spirit that inhabits you. For Aristotle, the soul is the organizing principle of the thing. It's the function of the thing, right? So if the eye were an animal, sight would be its soul. Sight is not a ghost. Sight is not a spirit. Sight is something that eyes do. It's the function that eyes perform, right? So when Aristotle's talking about a soul, when he's talking about the principle that drives a living creature, what he's really talking about are functions. And if we think about teleology in terms of functions, then maybe it's not such a ridiculous idea. In fact, maybe it's compatible with how we think about these things today, right? So, for instance, your heart, right? The function, your heart has a function. Its function is to pump blood through the system. It's part of the circulatory system. You need to have your blood in motion to transfer nutrients and oxygen to different parts of your body. And your blood and your heart is the main organ that does this. It does this through contraction, and the beating is what moves the blood around your body. So hearts have a function. Hearts are a natural system, like they exist in nature. Not just human beings have hearts, and it's certainly not the case that hearts are mostly made by human beings. Hearts were around long before any human being evolved, right? They were in our mammal ancestors long before we got here. So hearts are natural parts of the world, but they also have a function. They also do a task. They perform a role. There's a purpose to the heart. So how do you explain this? Well, on Aristotle's view, like there's a natural explanation. It's because all the things have a purpose. So everything has a function. Everything has a telos. So it's no mystery why the heart has a telos, because everything has a telos. Right? But how do you explain this on a modern scientific view? Well, one thing that a modern scientist is going to say is that functions are relative, and they're relative to the containing system. So the reason that the heart has a function is because of the role it plays in the organism. And so like if I were to cut the heart out of an animal and put it on a plate, that heart doesn't have a function anymore because it's not inside any organism. It's not doing any work for an organism. Right? A heart on a plate isn't doing anything. But when the heart is actually inside the organism, it's performing a role in virtue of how it fits, how it's situated, or how it's embedded in that organism. So in order to understand a function, you need to understand the role it plays for the containing system. Right, so here we have this sort of Aristotelian picture of the relationship between the part and the whole. That it's the whole organism that provides the context for understanding the part. And this is something I think I briefly mentioned last time, but Aristotle, the famous phrase that the whole is more than the sum of its parts. This is an idea that comes from Aristotle when he's talking about the organization of living systems. In fact, when he's talking about the organization of any substance, he's talking about something that as a whole is more than just its parts. The totality, as it were, is not merely a heap, but is a whole, something besides the parts. Right? So this idea that if you put the parts together in the right way, if you organize the parts, you get something more and not necessarily bigger, but you just get something more than you would have if we just had the parts by themselves. Right? This is exactly how Aristotle is thinking about the function and purpose of living creatures, that to be alive is to be more than just the matter that you're made of, but is to be organized into this totality where every part plays a role, performs some work for the organizing system. And so to understand the whole, you have to understand the parts and the roles they play. You have to understand the kinds of things that they are. Right? So to understand the heart is to understand what is it that things like this do. Right, so understanding the functional organization of the system, I think this is in fact, this is a very modern notion, and we'll see that for a long time, what happens in the scientific revolution is that this idea of a totality, of a functional whole, is rejected by science. For a long time during the scientific revolution, the idea was that you have to reduce everything to only the simple parts and the universal laws that operate on these simple parts, because there's no whole over and above those simple parts, right? And so this Aristotelian notion, it's exactly this Aristotelian notion of teleology that gets called into question by the scientific revolution. I think I said this in the last video, and I'm going to keep saying it. We have this image of the scientific revolution as being a revolution against religion, science versus religion. In fact, the scientific revolution is rejection of Aristotle. It's science versus Aristotle, and the key Aristotelian principle here is this teleology principle, this idea of a purpose. But if we understand purposes as functions, then maybe this is not so hard to understand. That maybe there are functions, maybe there are purposes in the real world. They're just functions. So let's think about these functions a little bit more. So the function of the heart is to pump blood. but like a dead person still has a heart. You put you bury them. You have a funeral and you bury them. There's still a body in there. Maybe that body still has a heart. Maybe the heart is removed during the embalming process or something. But maybe there's still a heart in there. Or if you take the heart out and put it on a plate, it's still a heart, but it's not. It no longer has the soul of a heart because it's no longer performing the function of a heart. Of course, there are. You all probably know that there are artificial hearts. That there are different ways that we've engineered biomedically to compensate for heart failures or different sort of heart problems. So an artificial heart is not made of the same thing as a real heart. An artificial heart might be made of plastic or stainless steel or something like that. But an artificial heart performs the same function as a real heart. So consider, for instance, Dick Cheney's heart. This is a graphic from the New York Times describing Dick Cheney's heart. Dick Cheney's had multiple heart attacks. So he's had to have quadruple bypass surgery. So all of the different chambers of his heart's basically non-functional. And so what they've done instead is they've attached this pump system to Dick Cheney's heart. So this is true. This is real. The flow of blood into the heart is bypassed and put through this pump. And the pump is a little electronic pump that moves the blood around in Dick Cheney's veins. So he still has his biological heart in his chest, but it's basically just a flap of skin used to contain the blood as it's flowing around. But the heart itself is not doing any work except just letting the blood flow through it. What's doing all of the functional work of a heart is this mechanical pump that's again, it's inside his chest, but then there's a little a cord that leads out to a battery, and he has to carry around a little battery pack on his waist and like a little fanny pack, and that controls the heart, and it he can change batteries and so on with this little external thing. Using this, Dick Cheney's been alive for several years with this artificial heart. Dick Cheney does not have a functional biological heart. His heart is entirely this mechanical alternative. So does Dick Cheney have a heart? Well, yeah, he's got an artificial heart. It's not made of the same stuff as a heart. It wasn't evolved biologically through genetics, right? This is an entirely mechanical, artificial device. It's Dick Cheney's heart. But today we would say that, well, he has an artificial heart, and what matters about the heart is not that it's made of the right stuff, or that it has the right purpose in some grand sense. The point is just that it performs the right function. Right? The role of the heart in the body is to pump blood, is to keep the blood flowing, and Dick Cheney has a system in his body to do exactly that. It pumps the blood. It makes blood flow. But there is a difference. There's an important difference. So Dick Cheney's heart, the artificial heart here, it's a continuous flow model. It moves blood continuously through the system at a constant rate. What that means is that there's no heartbeat, right? His heart, right? The reason that your heart contracts and expands is because that's what's doing the pumping of the blood around your body. But Dick Cheney doesn't need the heart to contract and expand to pump blood around because he's got this continuous flow model that's just constantly moving blood around his body. So that means he doesn't have a heartbeat. If you were to feel on Dick Cheney's chest, you would not feel any heart beating. You might feel like a little hum whirring of the pump. If you were to put your fingers on Dick Cheney's wrist in order to feel his pulse, well, Dick Cheney doesn't have a pulse because the pulse is an artifact of this expanding and contracting of your heart. And if your heart's not expanding and contracting, then you're not going to have a pulse. So part of the point here is that Dick Cheney's heart, it's a functional alternative in some respects, but it's not a completely functional alternative. There are some functions that the original biological heart performed that his artificial alternative does not perform. It doesn't have a pulse. And what that means is that you can't rely on Dick Cheney in other ways that you might not expect. Like, we use the pulse to tell if someone's alive. If someone's passed out and you think they might be dead, you go and check their pulse to see if they're alive. But you can't do that with Dick Cheney, right? If Dick Cheney passes out, if he's asleep, and you think that he might be dead, and you go check his pulse, you're not going to find a pulse there anyway because he doesn't have a beating heart. If you're looking for a pulse, you might conclude that he's dead. But Dick Cheney's not dead; he's still alive. It's just that he doesn't have a pulse. So this is like a downstream ramification because Dick Cheney doesn't have a standard biological heart, you can't use this other trick that is typically used with people with standard biological hearts. Does that matter? Does that make it less of a heart? You might think that the pulse, is convenient, but it's not strictly necessary. What really matters is just that the blood's flowing around. As long as the blood's flowing around, Dick Cheney can stay alive, and that's all he really cares about. If the sacrifice for staying alive is that you lose a pulse, it's not such a sacrifice. But, this raises the question, well, is there anything essential to the heart that, or to anything that characterizes the kind of thing that it is? How do these functions relate to this essence? Is there an essence at all? You might think that functions attach arbitrarily to things, that sort of anything can have any function if you use it the right way. Like I can use I can use a rock as a paperweight. I can also use my phone as a paperweight. I can use my cat as a paperweight. Maybe not a very good paperweight. My little nephew, I can use as a paperweight. Obviously, my nephew wasn't born to become a paperweight. That's not something essential to the person. But I can use it that way. In fact, if I'm clever enough, maybe I can use lots of things in lots of different ways. So, at what point is it a function of the thing? Does a function of the thing reflect an essence or a purpose or some deep purpose? Later on, and especially in the next video, I'm going to try to give a view of functions where you don't need any talk of essence at all, and that functions is just a discussion of the relationship between systems and other systems, especially systems that they're contained within. So sort of if you have a sort of natural hierarchy of systems, some embedded in others, then you can talk about functions in terms of these embeddings without talking about essences at all. But we'll get there later. So the idea is that there's something right to this functional perspective that Aristotle's developing. But there's also a lot of things wrong with it. It's exactly this functional view. Let me get myself out of the way here. It's exactly this functional view that, it's exactly this essentialist view that makes Aristotle think, for instance, that Earth is at the center, and then water and air and fire, and there's this sort of natural hierarchy of the elements. It's also what makes Aristotle think that there's this natural hierarchy among the living beings, sort of plants first, and then animals, and then like lower animals like insects, and then higher animals up to the birds, and then human beings, and so on to the angels and God. Right? The idea that there's this natural hierarchy in nature, and that this natural hierarchy is also reflected in the metaphysical structure of the universe. Right? This is all a product of Aristotle's metaphysics. The functional aspect of his biological system, it's interesting, but it's just a small piece of this much larger picture, and there's big reasons for rejecting this much larger picture. Again, I want to say the sort of picture of racism and sexism that we were talking about earlier arises from this sort of great chain of being. So maybe the functional aspect of Aristotle's biology is not enough to save the view. Here are bigger reasons maybe to reject the Aristotelian view. I mentioned this a little bit. Again, the elemental theory implies a kind of geocentrism. Earth is at the center of the universe, and all of the stars and the sun and the moon and all the planets revolve around Earth, according to Aristotle. And this is supposed to make sense on the basis of the elemental theory, because Earth is the thing that wants to be the lowest. So if I'm wondering why certain things fall, I don't know if I have anything made of Earth. Maybe the can of peanuts is made of Earth. And look, if I let go of the can of peanuts, oops, it'll advance my slide. Okay, wait. So the idea is that if the can of peanuts is made of Earth and Earth wants to go down, this is what explains why things fall down. Things fall down when they're made of Earth. If they're made of a lot of fire, then they might rise. Right. So this is why if you're burning a fire, then like ashes rise and so on, because they're made of more fire stuff than Earth stuff, and so they rise. But things that are made of more Earth stuff fall, and things made of water or air sort of sit in the middle. And this is this idea of sort of natural motion, that the elemental constituents of a thing determine how it moves. Again, there's many kinds of change and motion as there are kinds of being. This is Aristotle's sort of It's his physics, and sort of the metaphysical justification for this physics. So again, Aristotle talks about natural motion and not unnatural motion, but forced motion. So natural motion for an inanimate object is something that follows its elemental constitution. So when I drop the earthen thing, it falls down to earth. Right? So there's no theory of gravity. There's just the theory of things that are made of earth, and that earth has this natural motion to be at the bottom. And that explains why certain things fall to the ground. But also natural motion for animate things. Natural motion for animate things is going to follow not their elemental constitution, but their teleological constitution. So the acorn develops into the oak tree is the natural motion for the acorn because of the kind of thing that it is. But Aristotle also has a notion of forced motion. So the earthen thing, I can also lift it up. I lift it up. So earthen things fall down. The natural motion for earth things made of earth is to go down to the bottom. But here I am lifting the earthen thing up, and that's because I'm forcing it to do something that's unnatural to it. It's natural for the thing to go down, but I can move it in a contrary way. And so Aristotle has this whole theory about how this sort of natural motion and contrary motion complement each other and then explain all the different kinds of motion that we see. This explains not only the movement of physical objects, like why objects fall down, but it also explains the motion of the stars and planets in the heavens. It also explains the development of biological creatures. Of course, this whole idea is wrong. We talked a little bit about the problems with spontaneous generation and Aristotle's theory of reproduction last time. But right now I want to talk even more basic at the level of physics. So Aristotle has this view that Earth is at the center and that all the planets go around the Earth. And Aristotle also thinks that all the planets go around the Earth in perfect circles because it's in the nature of these eternal objects in the heavens to move with eternal motion, and so they move in these regular cycles forever. If it wasn't a perfect circle, then the cycle would go off all wobbly. So Aristotle thinks that rationality demands that the orbits of the planets are orbits in perfect circles. The thing is that when you actually measure how the planets are moving, they're clearly not moving in perfect circles. One thing in particular that planets do that's really strange is that they undergo what's called retrograde motion. So if you look at a planet in the night sky over several days, you'll see that the planet will start moving in one direction, and then it'll go retrograde. It'll start moving back in the opposite direction. In fact, this is how the ancient astronomers knew that the planets were different from the stars, because the stars all seem to move on a fixed background. The stars all seem to move together as like a fixed background, but the planets don't move together with the rest of the stars. The planets start moving with the rest of the stars, but then eventually stop and start moving back in the other direction, and then eventually stop and start moving back in the other direction again. And so when they go in reverse motion, so they have their typical motion, but then they also have this period where they're going in the reverse direction. And this is called the retrograde motion. And this is why the planets are distinct from the rest of the stars, because they're the only things that they're the only dots in the sky that are going in these retrograde patterns. But why are they going the retro? But by the way, this is why we call them planets. Planet, the Latin word planet means wanderer. So the planets are the wandering stars. They're the stars that don't move with all the other stars, but that they have this little retrograde motion. Well, so how do you explain this? Especially, how do you explain this if you assume the theoretical constraint that all of these heavenly bodies have to move in perfect circles? It's a hard problem. The ancient Greeks were really good with geometry, but they couldn't figure out really how to get this to work. Eventually, the idea comes around that there are these things called epicycles. So if this is the planet, and the planet's orbiting around the Earth in this direction, the idea is that the planet's not actually at point. In this diagram. So here's the Earth, this blue dot, and the idea is that there's a planet orbiting around the Earth. And everything has to be a perfect circle, right? So the idea is that, first of all, the Earth is not at the absolute center of the circle. The Earth is offset from the center a little bit. Why? Well, because this is the only way to explain the motion of the planets. If you think about it, the whole point of having the Earth at the center is because this is how the elemental theory says that Earth should go. So if you already have to move the Earth off the center in order to make the theory work, you can already see the sort of beginnings of a contradiction, or at least an anomaly. But so the idea is that the Earth is sort of off center, And then it's orbited by the planet, but it's not directly orbited by the planet, but there's this orbital path for the planet. But then the planet itself moves in a little circle around that orbit. Right? So the idea is that the planet's here, and so it sort of swings around in like a little spiral graph motion. You can see here, this is a picture of the motion of all the different planets. Each one of these different lines here is a different one of the planets. This one's the Venus orbit, and so you see the Venus has this sort of long looping orbit that goes around and around the sky. And the reason for this, the explanation, is that it's because the Venus, the orbit of Venus moves in one direction, but then Venus also has an epicycle that orbits around that orbit. So the planet is sort of moving in this spirograph motion around its perfect circle orbit. And it's a different spirograph motion for each of the different planets. And so this is all the different planets here. So this is how the ancient world thought about astronomy. A lot of the work, a lot of the like hard calculations and observations being done were just to track down and nail down exactly how these epicycles worked in order to be able to anticipate the movement of the planets around the sky. Remember, it's the movements of the planet around the sky that also impact things like your astrological sign and sort of other predictions that people are making on the basis of the stars in the sky. So getting this stuff right was what a lot of astronomy was concerned with. Exactly what is the orbit, exactly what is the epicycle period length, right? What is the radius of that epicycle? These are the sort of questions that concerned ancient astronomers. And the thing is that it worked. So we know today that this is not the physical situation with the planets. In fact, the way that it works in the solar system is that the sun is at the center of the universe, not at the center of the solar system, not the Earth, and that everything, all the planets, including the Earth, orbit the sun. And when you switch the perspective from the Earth at the center with all these complicated epicycles to the sun at the center, then you get very nice, clean elliptical orbits, and all of the math sort of clicks into place. The thing is that they spent 1,000 years working on this epicycle system, and it worked pretty well. You need these really complicated equations. You need people who are extremely good at geometry and the geometry of curves in order to calculate the very complicated paths that these planets are going to take. But the Greeks could do it, and the philosophers and scientists afterwards, the astronomers who came afterwards, were really good at these kinds of calculations. And they built these very elaborate star charts that helped people navigate the globe, right? When the original colonists were going out first to circumnavigate the globe, just to sail a boat around, and then to start colonizing different parts of the globe, especially in the Americas. Most of this stuff was happening before we had any better idea of how the stars and the planets were moving. Most of the star charts that these early sailors were using were based on these epicycle patterns. And again, it was good enough to navigate yourself more or less in the ancient world. And so not only were astronomers familiar with the epicycle equations, but so were sailors who were using the planets in order to chart their path through the waters. So this wasn't just a made-up theory that has this sort of mystical justification for it. This was the practical workaday theory that people were actually using in the world in order to do great things. And again, they circumnavigated the globe on the basis of this sort of epicycle theory. But as I said earlier, the whole point of the Aristotelian theory is to put the Earth at the center and to explain why things fall down. And you can see that the way that you can actually make this theory work is by offsetting Earth from the center and then having all of these other cycles and all these other circles, and therefore these other centers where Earth isn't, right? There's no Earth here. Like, why is this planet orbiting around this point when the whole point of the theory is that Earth should be at the center? So clearly there were problems with this view, and people recognized that there were problems with this view almost all the way back to Aristotle's time. There were some people who proposed alternative frameworks, including frameworks that put the sun at the center. But people really couldn't get over the idea that if the sun was at the center, that means that the Earth was moving around the sun, and that means that the Earth was moving really fast. And people thought, well, it doesn't feel like the Earth is moving really fast. If the Earth was moving really fast, we'd probably be flying off the Earth, but we're not doing that. We're not getting dizzy, so it's probably not the Earth moving. People were were fairly convinced that it wasn't the Earth moving. Again, it was proposed, in fact, several times it was proposed, but it never really got popular. The geocentric view, the one where the Earth is at the center, sometimes called the Ptolemaic view. Ptolemy was an astronomer and wrote some books about how the system works. And these were the books that were widely discussed, and this is a theory that was widely believed throughout the Middle Ages for a very long time. Wasn't really definitively disproven until Galileo. This change from the geocentric worldview with the Earth at the center to the solar system with the sun at the center, the heliocentric worldview, is called the Copernican revolution after Nicholas Copernicus, Copernicus was not the first person to hypothesize that the sun was at the center, but Copernicus did work out some of what that meant in some detail in the early 1500s. And these ideas were going around, but there weren't any real proofs one way or the other. There weren't really any proofs one way or the other until the late 1500s, when people started getting really serious about scientific observation. In particular, an astronomer named Tycho Brahe, who himself believed in the geocentric solar system, or the geocentric universe. But Tycho Brahe had an observatory with some of the most high-tech astronomy equipment of the day, and did very detailed observations of the planets and of the different stars. The most detailed observations that had been done at the time. One of Tycho Brahe's students was Kepler, and Kepler helped develop these star charts along with other people who worked at the observations. And Kepler eventually uses these star charts to develop his laws of motion. Kepler also believed in a geocentric universe, believed the Earth is at the center, but started working out equations for thinking about elliptical orbits and how to describe the motion of the planets in terms of elliptical orbits. Kepler sets out some laws of motion. They're very rudimentary laws of motion, but they get developed later by Newton. The other big thing that happens around this time, early 1600s, is Galileo. Galileo has the bright idea of using these new telescopes to look up at the stars. So not just observation by naked eye, but Galileo starts doing astronomical observations with his telescopes. Telescopes had been invented by sailors to look at other ships at sea on the horizon, but Galileo was using his telescope to look up at the stars. And what Galileo sees are moons around Jupiter. This is Galileo's sketches in his notebooks of his observations of Jupiter. And what he notices is that there's other little stars around Jupiter, and they move. If you look at them today, they look like this, and if you look at them tomorrow, those stars around it are in different positions. And it's pretty clear after his observation over several days, over about a month period, that these little stars are orbiting around Jupiter. And no one had ever seen this before, but Galileo sees it with his telescope. And if there are moons orbiting around Jupiter, right? Again, remember, the whole point of the epicycle theory is to put Earth at the center and have everything orbiting around Earth to some extent. But if there are moons around Jupiter, that means that there's some other center of center of gravity. Galileo wouldn't use that term. It means there's the center of orbit. Some things are orbiting around something that's not Earth. Right? The stars are orbiting around Jupiter. This is like a major breakthrough. The idea that Jupiter has moons. These are the so-called Galilean moons. There's 4 of them that Galileo was able to observe. And these Galileo moons eventually convinced Galileo that Copernicus is right, that the sun is at the center of the solar system, and that everything orbits around the sun. Galileo is operating around the same time as Kepler. I don't think Kepler ever adopts the heliocentric view. Maybe I'm wrong about that. But this early work, this early work that's seriously driven by observation, by very meticulously kept star charts and observations of the moons of Jupiter and so on. This all builds over the next century, so that by the end of the century in 1687, Newton has turned Kepler's laws of motion into universal laws of gravity. And Newton is able to explain the orbits of the planets around the sun, and therefore the motions of the planets that we see in the sky, in terms of these mechanical forces. Oh, I'm blocking the thing again. In terms of a law of universal gravity. And this is the important part for our purposes. The law of gravity doesn't depend on kinds or natures or essences. Remember, Aristotle says that there are as many different kinds of change in motion as there are kinds of thing. But what Newton discovers is that, no, in fact, there's a universal law of motion that applies to all things with mass. Just having mass, mass at all, is enough to make you susceptible to the force of gravity. And that this force of gravity not only explains why things fall to the ground here on Earth, but that same law also explains why the planets move around the sun, and why the moons of Jupiter move around Jupiter the way they do. Right? That all of these kinds of motions, both on Earth and in living creatures and in the heavens, that all of these kinds of things are explained by one single universal law of motion. This is Newton's law of gravity. So it's G and M, that the force here equal and opposite, and the force here is this universal gravitational constant times the mass of the first times the mass of the second over the radius squared, distance between them. So you take the two masses, you multiply them together, you take the distance between them, you square it, you take the masses over the distance squared, and then you times this by this universal constant, and that will give you the force between them. So if these are two massless objects, if they have no mass at all, then the force between them is just the gravitational constant over the distance between them. Times zero, because there's no mass. But as the masses grow, you get this orbiting relationship. And especially when one mass is much bigger than the other, as is the case with the Earth and the Sun, you have orbits that look like the elliptical orbits that you see with the planets, with Earth and all of the other planets that we can see. This is what kills Aristotelian teleology, Newtonian mechanics. Newtonian mechanics gives a demonstration of a law that's universal in nature and doesn't depend on the kind of thing that it is. Right? So you don't have to describe different kinds of motion for all the different kinds of thing. Here we have a universal law of gravitation that affects all things with mass equally. You might think, well, maybe the things with mass are a kind of thing, but the mass is just the matter. This is not a theory of light or the relationship between light and matter yet. This is just a theory of matter. Anything with mass is going to be subject to the same law. The motion of even inanimate things like human beings are explained by the same universal laws that explain the motions of rocks and planets and stars. Instead of the natural motion of Aristotle, the motion that's set by the kind of thing, what Newton puts in its place is a fundamental property called inertia. Inertia is the tendency of an object in motion to stay in motion. If an object's in motion, it'll stay in motion unless another force acts on it. Again, this is not what Aristotle thought. Aristotle did not believe in inertia. Aristotle thought that if an object is in motion, you have to continually apply a force in order to keep it in motion. If you don't continually apply a force, then it'll settle in its natural space, in a natural place. Right? So again, this is why the earthen thing falls to the bottom and finds its settling place, because it has a place that it's aimed at, sort of the place where it's supposed to be, its natural place. And the thing will move until it finds that natural place, and then it'll stop. But for Newton, there's no natural place to things. There's just inertia. There's just the tendency to stay in motion unless another force acts on you. So if we're out in space, if we're not next to Earth or any other big gravitational well, and I throw something, then that object will keep going forever, and I don't need to keep applying force. I don't need to keep adding forces to it. That thing will keep flying forever on the trajectory that it's on. It might get pushed this way and that by different gravity forces. Right? If it gets close to a star, that might bend its trajectory one way. And also the ball will be hit every once in a while by atoms and cosmic dust and so on. That'll slow it down, provide some friction to slow it down. But these are other forces acting on that motion on that object as it moves. If those forces were taken away, then that object would keep moving indefinitely at that rate. So this idea of inertia is entirely foreign to Aristotle's theory of motion. There's no such thing as inertia. Inertia is a brand new thing that Newton introduces, and inertia is what all massive objects have in common. It's a fundamental property of matter. It's a universal property of matter that doesn't depend on kind, doesn't depend on nature, doesn't depend on essence. And it works spectacularly well. The physics, all the technologies that we have around us are the result of understanding the physics of the everyday world to an incredibly high degree. But even in hundreds of years ago, we had some good, strong evidence that this Newtonian theory was right. Maybe the best example of a vindication of Newtonian mechanics over the Aristotelian view. I mean, Newtonian mechanics, it could make predictions. It could make very accurate predictions about when eclipses would happen, about where the planets would be at various points in the future. And you can even predict it well into the future with very high accuracy. The high accuracy and the simplicity of the heliocentric model of the solar system is what made it win out. It became very useful for navigation and so on. But there were a couple of just mind-blowing proofs or demonstrations that convinced everyone that the Newtonian system had to be right. A really big one is the discovery of Neptune. So we had known all the planets through Saturn, and then after careful observation, we eventually found Uranus. Uranus is pretty dim, and you can't see it with just the naked eye. You need a telescope to see Uranus. But we eventually saw it, and we were trying to work out exactly what its orbit would be, Uranus, and using these Newtonian equations. And the equations gave predictions that just didn't line up with where Uranus actually was in the sky, and people couldn't really figure out why they weren't finding Uranus where the equation. All the other planets seemed to be working well with these equations, but Uranus wasn't working well with the equations. No one really figured out why. And then someone hypothesized that maybe there's another planet further out that's slightly tugging on Uranus, and that this is why Uranus is sort of lagging behind its predictions. So they worked out the equations, and someone figured out how big the other planet had to be and where it would have to be in order to make this kind of adjustment to Uranus's orbit. So it was predicted in the 1820s, and people went around looking for it, and eventually someone found exactly that planet where they thought it would be from these mathematical predictions. Right. So using the equations, they predicted that there was another planet out in the sky, and then they found that in fact, yes, there was that planet there. Right. So it was just the math that was guiding this research. But the math was strong enough that when you looked where the math told you to look, you actually found a planet there. And that blew everyone away. Being able to predict solely on the basis of these equations that there's a whole other object in the sky, this giant planet in the sky, was a phenomenal achievement, historical achievement. In fact, people got a little bit carried away with it. So the same guy who made this prediction that Neptune was responsible for the deviations in Uranus's orbit. Well, there was another problem with one of the planets, which was Mercury. That Mercury was orbiting in a way that wasn't exactly to the equations of Newton. The deviations weren't as bad as with Uranus, but there were deviations from the predictions based on the Newtonian model, and people didn't know why. So the same guy who predicted that Neptune exists also predicted another planet that was between Mercury and the Sun. It's called Vulcan. It's supposed to be a very hot planet. If you know from Star Trek, the Captain Spock is from Vulcan. So Vulcan is this hypothesized planet that's supposed to exist closer to the Sun than Mercury. And it was supposed to explain the deviations in Mercury's orbit. And the guy who predicted Neptune and then was vindicated spent the rest of his career looking for Vulcan and never found it. And he never found it because it wasn't there. We know now that the deviations in Mercury's orbit are not explained by another solar body near the Sun, but it's instead explained by the difference between Newtonian mechanics and general relativity, Einstein's equations. Einstein's equations and Newtonian mechanics match up for the most part for most sort of medium-sized objects around us. But when you get to really, really big objects or really, really fast motion, then the equations differ by a little bit, and the amount that they differ is just enough to explain why Mercury doesn't meet up exactly with the Newtonian predictions. Okay, so Newton was predicted and then discovered a long time ago on the basis of this math, and we've done a bunch of other things since then. Maybe my favorite example of the vindication of our physical theories about planetary motion is the New Horizons spacecraft. This is the New Horizons spacecraft that we shot out to Pluto, and Pluto is something like 32 astronomical units away. 1 astronomical unit is the average distance between the Earth and the Sun. So New Horizons is a spacecraft that we sent out 32 times the distance between the Earth and the Sun, way out there. By the time it hit Pluto, this is a 9 light hour travel. So it would take light 9 hours to get from the Sun all the way to Pluto. It would take 9 hours for light to travel that far. So we were able. So Pluto was out there. We sent a spacecraft out to rendezvous with Pluto, and that trip took 10 years, and we ended up within 7,800 miles of Pluto, which in astronomical terms is like grazing right by it. We were able to take some pretty high resolution pictures of Pluto. New Horizons it's going to keep going. It's seen a couple of Kuiper Belt objects in the time since. It's actually readjusted its flight path to swing closer to some of the bigger Kuiper Belt objects out there. And it's still going. I think we're going to still get information back from it. But the idea is that it's a proof by demonstration that we know what we're talking about. If you can shoot a rocket into the sky with such precision that you know that 10 years later it's going to fly this close to a planet 32 astronomical units away, like to be able to pull off that kind of scientific and engineering feat, you have to know what you're doing. You can't be so terribly confused about what you're doing. Aristotle couldn't have done something like this. Aristotle's theory of causation, Aristotle's theory of astronomy and of natural motion is not equipped at all to do this kind of technical feat to get a satellite to Pluto. But the equations that we have now, Newtonian mechanics and general relativity, is exactly what you need to get something to Pluto, and we've done it. Like you can see the results. It's sort of amazing. So this sort of vindication of the Newtonian picture gives rise to the second of our explanatory models. This is the second sort of slide of these models. This is the Newtonian or classical mechanics picture. It arises in the 1600s with Galileo, sort of Galilean astronomy, Kepler, and so on, and through to Newton, and then ends in maybe the mid 1800s, mid 19th century, with the rise of thermodynamics. So, in fact, this sort of classical mechanical picture is only a brief period in the history of the philosophy, couple of 100 years, 150, 250 years maybe. This is also the period of global expansion and colonialism. And then afterwards, we sort of get the Industrial Revolution. So, okay, but the Newtonian mechanical picture is just the idea that, look, this Newtonian framework for explaining gravitational motion is just, this is how science works. And this is really the goal of science, is to explain the world not in terms of essential kinds and teleological structures, but instead in terms of simple parts and laws that operate on these simple parts in law-like ways, in regular ways, these sort of universal rules that determine exactly what happens to these fundamental parts. Right, so the Newtonian picture is deterministic, it's reductionist. Deterministic in the sense that what happens next follows necessarily from what happened before. So think of like a series of dominoes, right? If I knock down this domino, then it's going to knock down this domino and knock down the next domino and so on down the line. And so once I started the chain reaction, then it's inevitable that these later dominoes are going to fall. From that initial start and the way the whole system is set up, you just get this chain reaction of events. And every event that happens is determined by every event that happened before it. Right? So you have this completely determined sequence of events. And to explain that sequence of events, you want to understand the fundamental, the atomic units of the system, right? What are the fundamental pieces of the system, and the rules that operate on the systems. So this is my diagram for the sort of rule-like state transitions for Newtonian mechanics. Right? We're in this state, and then there's some universal law that takes us from this state to this state, and there's some universal law that takes us from this state to this state. Maybe it's the same universal law operating at every step, and so we're sort of going from one state to the next, from one moment to the next, in this entirely deterministic law-like way. Right, so by state here, these little circles are the states. And by state here, I mean just the complete physical description of the universe in terms of its simplest parts. Like, where are all the atoms? What is the position and momentum of all the atoms? Right? If you have a position and momentum value for all the atoms, then you have a complete state diagram for the system, or a state. You have the complete state description for the system. And then you have the rules for how do these particles with some position and some momentum, how does that system evolve over time? Right? Like, where does it go next? How do these particles interact with each other, and so on? Right? These are the universal laws that determine how one state moves to the next. And the transitions here are necessary. They're deterministic, that if you're in this state and you get this law applied, then you're necessarily in this next state. This is the reductive mechanical view. Sometimes people think that this is just the scientific view, and I'm going to argue a bit later that this is not how science thinks about the natural world today. But maybe this was a popular view in this sort of brief period, 17th and 18th century, early part of the 19th century. One aspect of the Newtonian picture, though, is that it's a complete rejection of this idea of functions or purposes. For the Newtonian, for the mechanist, the world is made up of a bunch of particles and a bunch of rules operating on those particles, and that's it. There's no grand purposes. There's no designers. There's really no functions except in as if sort of sense. Like there's no a goal for human life in any grand sense. What a reductionist determinist like this would say is, well, you're just a pile of atoms operating according to these universal laws. I guess nowadays we'd say that you evolved over time in order to like happiness and dislike suffering. And so you have evolved in ways to prefer suffering, or prefer happiness to suffering. So you're going to act in these ways, but you're determined by that, by your genetic code, by your biological structure. And so you just happen to act in ways that maybe that aim for the good life in some sense, but they don't guarantee that you're going to get there. What really is going on is that, just so we like talking about that, the way that our brains work is that we can make sense of the world by thinking about it in terms of these functions and purposes. But then Newtonian's going to say, but these functions and purposes don't really exist. There's no purpose to life. And in fact, maybe there are really no organisms at all, that an organism is just a big, complicated pile of atoms, and that all you really need to explain is how these atoms behave, how the atoms interact with each other. To us big mammals, it looks like there's organisms and there's these higher level processes. It looks like things are thinking, and there's these big higher level properties, and like things like the United States of America and love and this kind of stuff. But these are all just fictions. These are all just stories that we tell ourselves to help explain to our big primate brains about how the universe works. But those are just stories. None of that stuff really exists. Love doesn't actually exist. What does exist are little chemicals in your brain that move around. The United States doesn't really exist. What really exists are a bunch of atoms moving according to these universal physical laws. We like to talk about it in terms of these abstractions like the United States of America, but they don't really exist in any physical sense, in any meaningful sense. So there are no purposes. If Newtonian science, if modern science agrees on anything, it's that Aristotle's notion of the soul doesn't exist. There's no soul inside you. There's no higher purpose or function inside the mechanical operation of all these parts. Right, so you get from this a picture of agency, a mechanical picture of agency, where agency is sort of locked in by these different sort of structures in the body. Let me get myself out of the way here. Sorry. by these different physical structures. So you might think that the physics and maybe my chemistry constrain me to act in specific ways, and maybe my biology and my genetics further constrain me to even a more narrow set of actions, and maybe my psychology, my neuroscience, but also like sort of how I've developed over time in my childhood. Maybe all of these are constraints on my behavior that are sort of locked in and determined by these aspects of the natural world, by the aspects like my biology and how my brain works, the society I'm born in, and so on. Right. So this determinant. So there's first this idea of determinism that each of these each of these conditions sort of sets how you're going to behave, or sets what you can do, sets how you're going to act. But moreover, that not only are these things determined, but they're also reductive. That in order to explain the effect of the childhood environment or whatever, you can explain that in terms of operations on brains, in terms of neuroscience, in terms of neurochemistry. And maybe the neurochemistry itself can be explained in terms of genetics and DNA and evolution. And maybe the genetics can be explained itself in terms of molecules. After all, a gene is just a big molecule. And so if you know how all the atoms in that molecule are acting, then maybe you can predict everything that the gene's going to do. And then maybe you can predict everything that the brain is going to do, that the individual is going to do, maybe even what the society is going to do. Right? So this idea that the deterministic mechanical framework locks in behavior at these various levels, and that each level can be described or explained in terms of a lower level. So I think this is still a rather popular view, or at least you see it expressed pretty widely. Here's a little XKCD comic. Elaborating on the view. Right? So these are fields arranged by purity. On the far left, you have the sociologists, and then you have the psychologists. And the psychologists are saying that sociology is just applied psychology, and the biologists are saying that psychology is just applied biology, and the biologists are saying that biology. I'm sorry, the chemists are saying that biology is just applied chemistry, and the physicists are saying that chemistry is just applied physics. And the physicists think that it's nice to be on top, and then the mathematicians over there saying, "Hey, I didn't see you guys way over there." And then outside the box is the philosopher saying, "How come we're all in the box?" And this idea that there's like a natural hierarchy to the different fields of studies, different fields of inquiry, and that every field of inquiry sort of bottoms out on a lower field of inquiry, and this sort of goes all the way down. So I think this is a fairly standard view in the sciences. Maybe engineers also think this to some extent. I guess I want to say that this is not a novel view, and in fact, in some ways, this is just another variation of this great chain of being, that there's a natural hierarchy to the world. I have some quotes from some determinists that might be worth looking at. Leibniz was a determinist in some sense. We'll see that he has interesting views of what it means to be alive, but Leibniz says straight up that the world is a great machine, and that it operates without the interposition of God, as a clock continues to go on without the assistance of a clockmaker. Is a notion of materialism and fate, and tends to exclude the providence of God and God's government in the reality of the world. Something's going on with that quote. I think I might have. Maybe that's not the best quote. Leibniz thinks that the world is a great machine, and the image of the machine here is as a clockmaker, right? So a clock or a watch is a highly designed, intricate piece of machinery. You have to have a skilled technician, a skilled craftsperson to build that watch to specifications so that it operates just right. And in order for it to operate just right, you need every piece of it to be hooked in just the right way to all the other pieces so that the clock keeps good time. In the 16, 17, 1800s, when this stuff is being discussed, the clock is like the most important technology. Clocks are essential to any kind of travel, or sailing requires clocks so that you know what time it is, so that you can to read the stars correctly. Is how you know what latitude line you're on. So the clock is an incredibly important piece of machinery. It's also a social machinery. Like, societies sort of organized around the assumption that people have clocks, and that you can clock into work at a certain time and out at a certain time. The church meets at a certain time, and so on. So it's an incredibly important piece of technology that they interpret their entire world through. And so the idea is that the universe is supposed to work like a clock. It's this highly designed, intricate piece of machinery that works just so, if you set it up right, if you design it well. Now, the interesting thing about a clock is that if you make it well, then it just needs a little bit of maintenance. You need to wind it every day. But if you do the winding every day, then the clock will continue to run and keep good time for the life of the clock. And this is a common idea in this period, sometimes called deism. Deism is the view that God, there might be a creator God, that there might be a God who created and designed the world, maybe designed the world to be a very elaborate machine, but that otherwise, apart from creation, God doesn't interfere with the world. He doesn't intervene on the world. Doesn't make the world do this rather than that. That God sets up the initial conditions and then sort of kicks over the first domino. And then everything that happens after that is just the result of the natural structure that God designed. Just like a clock will keep ticking time, the universe keeps ticking along. It's not because God is making it tick along at every step. God sort of just knocked down the initial domino, and the rest happened because of the design of the system. One figure in this conversation is Laplace, and Laplace has a thought experiment where come to be known as Laplace's demon. And so Laplace's demon is a supreme intelligence who knows just a couple of things. The supreme intelligence knows the present state of the universe, and the supreme intelligence knows all the forces that act on the universe in a given instant that changes it from one state to the next. So my image over here of the Newtonian picture, maybe it's even better to call this the Laplacian picture. So the Laplace's demon is this supreme intelligence that knows what the state of the universe is right now and what the rules are that take the universe from this state into the next state. And what Laplace says is that if you just know these two things, the current state of the universe and the transition rule that takes you from this state to the next state, like how does the universe update from one time step to the next? If you just know these two things, Laplace realizes, then you can predict everything that happens in the future. Right? If I just know this state and the update rule, well, then I get the next state and I can apply the update rule again, and I get the next state and I can apply the update rule again, and so on. And I can predict as far into the future as you'd like me to. In fact, I can use the same procedure to predict, recall what happens in the past. Just applying the procedure in reverse gets me all the states in the past as well. Right, so Laplace's demon is the supreme intelligence that can do all these predictions in advance and knows exactly how the world will develop in the future. And this is, again, the point of this deterministic reductive view, is that as long as you have these fundamental parts, the basic constituents of the universe and the update rule that takes it from one state to the next, then you can predict everything that happens in the system. This is the reductive deterministic Newtonian classical mechanics view. Again, the view works. It works for a lot of really practical things. If you are making any kind of artifact, if you have any kind of if you're building anything, you're going to be using a sort of picture of functional organization, but that takes seriously the mechanical and physical properties of the thing. And understanding those physical properties allows you to build all sorts of stuff. And indeed, when we build these tools and technologies, we think about it in functional terms, teleological terms. We think that different parts have different purposes. Right? Like just like your heart has the purpose of pumping blood, the tires on your car have the purpose of helping you drive and maintain traction with the road, and so on. Right? Like the different parts of artifacts have functional purposes, and this is a very useful way of understanding artifacts, the things that we build. It's a really good way of planning how to build new things and improving on the designs. Understanding the functional structure of these things is really important for how we build artifacts. But, and we can build all these artifacts on this sort of mechanical picture of the universe. But does this apply to all things? Right? One of the big virtues of the Aristotle system is that it applies to all things. Okay, so maybe the Newtonian mechanics helps us explain physical objects and like the theory of gravity and why things fall down, and maybe it helps us predict the orbits of the planets. But that's not everything. Maybe that's just some things, and maybe some things cannot be explained by that Newtonian reductive deterministic method. In particular, maybe life can't be explained in this method. So the Newtonian picture gets developed in the 1600s. Newton is at the end of the 1600s. But from the 1600s through to the 1800s, people were very well convinced, including people like Newton himself, were fairly well convinced that the physical properties being described by Newtonian mechanics don't apply to all things. In particular, they don't apply to life, that you can't explain how life moves or how life works by just appeal to these universal mechanical laws operating on fundamental simple parts. Instead, people thought that you needed some other force, some other non-physical force, the vital force that explains why living things behave the way they do, why they grow and reproduce and die, why they're nutritive and sensitive, why they're rational like we are. Right? The idea was that none of those things can be explained by physical mechanisms, but that you need some vital force. I talked about this a little bit last time. Here's the definition of vitalism. There's some non-physical element that explains why living things work the way they do, or that distinguish living things from the non-living things or the inanimate things. Some fluid or spirit inside the body. Maybe a fluid or spirit is not exactly Aristotle's view, but after Aristotle, and especially in like the 1600s, once Newton's around and can explain the motion of the planets, there's this big drive to say that, well, we got to explain biological life by some other mechanism. It can't just be gravity. It's got to be something else. And again, this was the popular view. This was not just a superstitious or religious view. This was the going scientific view, that there was some vital force, sometimes called the élan vital, the vital spirit, the vital force. And the thing about the vital force is that it's not just this mechanical reductive process, but the vital force is teleological. The vital force is what explains the purposes of living creatures. And that it explains what makes the living creatures different from the mechanical systems, the sort of purely mechanical systems, right? And Newton believed this, Descartes believed this, maybe even Leibniz believed this to some extent, that the universe itself operates as a mechanical process at some level, but there are some things in the universe, like living creatures, that have other forces and maybe other properties, maybe other things like some fluid or some active power that explains the teleological and purpose-driven structure of living creatures. Maybe the height and most elaborate and sophisticated version of this is Lamarck. Lamarck is the pre-Darwinian theory of evolution. Lamarck eventually realized, the important thing about Lamarck is that he realizes that there's something wrong with the Aristotelian conception of different categories of things that are just separate from each other. And Lamarck has the idea that creatures change over time, not just in their matter, but also in their form. And Aristotle didn't think that, right? Aristotle thought they were just different kinds of things, and they stayed those kinds of things. But Lamarck has this idea that creatures change their form over time. And nowadays, we kind of ridicule this idea, especially the Lamarckian giraffe, right? So Lamarck thought that the reason the giraffes have long necks is because there was food up high to reach, and so they sort of grow their necks, they sort of stretch their necks over time, and this process of continually stretching your neck over generations yields giraffes with higher necks. This is how Lamarck thought of evolution. And we can see that this is a kind of vitalist or teleological way of understanding evolution. The idea is that the giraffe changes over time, that the form changes. So it's not exactly Aristotelian, but the direction that it changes is anticipated by the goals of the creature, right? So it's because the giraffe has the goals of eating these high leaves that over generations its neck stretches out. This is the idea. To be clear, Lamarckian evolutionary theory is wrong. It's decisively rejected by modern science. Nowadays, we believe in Darwinian evolution and the modern synthesis. And Lamarckian evolution is rejected. Right? This idea that giraffes grow their necks long because that's what's good for them is not exactly right. Nevertheless, this still infects the way that we think about evolution and evolution over time. There's still this persistent idea or image of evolution with the apes, where there's this sort of lower ape, and that the ape evolves over time into the higher creature and eventually this idealized form of the human being. Again, this is just the great chain of being. This is exactly the great chain of being. And modern evolution doesn't think this way at all. Evolutionary theory today does not think that a chimpanzee is a lower and less evolved form of a human being. right? Because that idea is that if you wait long enough, the chimp will eventually turn into a human. Through over the generations, the chimp will get closer and closer to the human form. This is just not true. Chimpanzees today are exactly as highly evolved as human beings today. They just evolved for a different niche. They just evolved in a different context with different evolutionary pressures. And so the chimps evolved in order to fit their niche, and we've evolved to fit a different niche. And so the differences between humans and chimps can be explained by this different evolutionary history, without assuming that there's some ideal form that we're all aiming towards. Right. So this view of evolution is wrong. It's bad. I don't want to propagate it at all. But you can see, hopefully, the sort of Aristotelian flavor of these kinds of sort of early views of evolution. That they're still sort of teleologically structured. That there's still sort of end or idealized goal or purpose. And we can see how this sort of debate between the vitalists and the mechanists play out. Maybe the best way to see this is by looking at a debate like are viruses alive? This might be a debate that you went over a little bit in high school biology class. For the most part, people today say that viruses are not alive. And why is that? Why aren't viruses alive? Well, let's talk a little bit about the structure of a virus. So here's coronavirus. We've been talking about for the last summer, since February, I guess, or since January. Oh, coronavirus. So a virus is a very simple little creature. Viruses have genetic material. They have RNA. Some viruses even have little bits of DNA. Or some mRNA. But the RNA is in a little tight packet, and then that packet of RNA is sealed with a membrane. And then on top of the membrane are these little spike proteins for the coronavirus. And the spike proteins are what allows the virus to attach to a cell, to open up the cell so that it can inject its RNA into the cell. Right. So viruses themselves are not doing any reproduction or development on their own. The virus doesn't have any metabolic processes. It's not burning energy in order to maintain homeostasis. The virus is just this molecule with a little package around it. And the package is designed to get it into a cell. And then once that molecule is in the cell, the molecule works just like all the rest of the genetic molecules in the cell. So that molecule can take over the replication process. It can hijack the ribosomes so that the ribosomes start reproducing this DNA as opposed to the cell's normal DNA. And it can hijack the machinery so quickly that the cell eventually produces a bunch of these viruses, and the cell breaks apart, and all these little viruses go off and infect another cell. So the virus doesn't have any metabolic processes. It's not growing and dying. It can't do any of the reproductive activity of being alive on its own. In order to do that, it needs the reproductive machinery of the host cell. So maybe that means that the virus is not alive when it's packaged in the little capsid, but maybe the virus becomes alive when it infects the host cell. Right, so maybe the virus has a dormant, non-living phase and then a living phase when it's infected in the cell. But then the virus doesn't look like this. The virus looks like a normal cell. It's just producing viral DNA as opposed to normal DNA. We know how viruses work to a pretty high degree of detail. In fact, some of the biggest simulations in biology are simulations of viruses. So when I was in grad school at University of Illinois back in 2006, they sequenced and did the first full-scale simulation of a living of an organism, of a virus. So this is a full-scale atom-for-atom reproduction. They simulated every single atom in the virus. So not just its genetic code and not just an abstract model of the virus, but they actually simulated the molecular structure down to the atom. And not only did they simulate the molecules in the atom itself, but they also simulated it, all the water molecules in a cubic centimeter. Not a cubic centimeter, it was less than a centimeter. It's maybe a nanometer. So 1 cubic nanometer of water with a cell inside that water. And they simulated on supercomputers every single atom in this whole system. including the water. This is about 1 million atoms, and they simulated its time evolution for about 50 nanoseconds. So how this system changes over time for about 50 nanoseconds. So like 50 little nanosecond jumps in time. And they're simulating this at atomic resolution using quantum mechanics, the best sort of quantum mechanical theories that we can simulate. So this is an atom for atom simulation replication of a full virus. This is a tobacco mosaic virus. More recently, just at the start of 2020, they had a supercomputer simulate a full H1N1 virus. So the full H1N1 virus, atom for atom simulated in supercomputers. This is the largest full atom simulation of a biological organism ever. This simulation simulated about 160 million atoms. It's like 160 times what we did in that first simulation. And they did it over a span of time of about 120 milliseconds. 120 nanoseconds. So it's not a whole lot longer, maybe twice as long as the original simulation. But the organism that we're looking at is much, much bigger. So these are cool if you're into computer simulations. We have full atom for atom simulations of very, very simple organisms now. And if this is any record of how fast this is developing, we should see even bigger organisms in the future being simulated at a full scale atom for atom scale. But as I said earlier, the virus doesn't metabolize anything. It has no active metabolic processes. And so a lot of people want to say that the virus is not itself alive because it's not metabolic. It doesn't do any of the reproduction or metabolism. So metabolism is the energy burning process of a cell. Right? Cells burn energy in order to maintain themselves. And there's a couple of different theoretical models for what exactly the cell is doing. This is maybe a very simple and kind of an old one. This is the chematon. So these are both examples of chematon. This is a more recent variation of the chematon. But so the chematon is a model of a cell. It's a sort of an idealized model of a cell. This was suggested by Tibor Ganti, who was a plant biologist in the 1970s. And Ganti was really just trying to think of what is the simplest sort of structure that explains how a cell operates. And on Ganti's model, there's really three core parts of the cell. One is this metabolic cycle. So there's a cyclical process that's an energy burning process that's energy burning that's autocatalytic, but it starts itself and it runs itself. So it's a self-running metabolic process. It's a metabolic cycle. In living systems, this metabolic cycle is the citric acid cycle. In fact, every living creature has as its core metabolism some part of the citric acid cycle. Some organisms only use parts of it. Some organisms have like a little piece of it that goes in the opposite direction and so on. But living organisms are built around this fundamental chemical pathway, this metabolic cycle, the citric acid cycle, the Krebs cycle. You might remember from biology. And so every cell in your body is running this metabolic process. And it's an autocatalytic process, which means it's a self-running process. It means that once it gets started, it just keeps going. It doesn't run itself for free, right? So this is not this organism is not isolated from its environment, but it's exchanging material, it's exchanging energy with its environment. So it's taking in new nutrients to feed that catalytic cycle. The cell needs to have a constant supply of nutrients to go into the cycle in order to create all the little molecules. And that process produces heat and it produces other waste products, little fragments of molecules and so on. And that also needs to be removed from the process. So the metabolic cycle is taking in nutrients and it's spitting out waste. It's thermally interacting with its environment. It's mechanically interacting with its environment. The environment is where it's getting all its stuff. It's where it's spitting out all its waste. But the cell is using that metabolic process to construct all of the other things that it needs to maintain itself. So for one thing, there's other chemicals needed in this metabolic cycle. Maybe some chemicals it can produce itself. So it can get some things from its environment, but other things it has to produce itself. And so some of those byproducts that are built from the metabolism go back into fueling that metabolic cycle. To some extent, the metabolic cycle seems like a perpetual motion machine, except it's not a perpetual motion machine because it's thermally interacting with the environment. So it's getting a constant supply of nutrients. And if those nutrients get cut off, then the organism dies. But as long as the organism can keep itself alive, then it keeps producing material, both to help run the metabolic cycle. So there's three components in the chematon. One is the metabolism. The second big component is the information storage. So information storage, like the genetic code, the DNA. And the idea is that the genetic code encodes regulatory constraints that are being used to manage the metabolic process. So the metabolic process is this very complicated process, and it needs to operate within certain parameters. You need to control it in certain ways. And the genetic code contains all the information, in particular like the proteins that you need to break apart the DNA and add other pieces of the DNA and so on. All of the code for that machinery, for manipulating and managing that metabolic process, that's all stored in the genetic or information repository. In most cells, this is RNA or DNA. So the DNA constrains and controls and enables the metabolism. And the metabolism keeps running as long as those constraints are in place. And there's one other big part of the chematon, which is the membrane. The metabolic process is delicate, and it requires certain conditions in order to maintain. The concentration of nutrients in the environment has to be a certain concentration, like in the concentration of ions in the environment and so on. All of that is a very delicate balance, and in order to maintain that balance over time, what the chematon does, what the cell does, is it constructs a membrane, a barrier around itself. The barrier isolates these processes from the surrounding medium through the semi-permeable membrane. So again, the cell is still taking in nutrients, it's still spitting out waste, but it's doing this from within a controlled environment. And because that environment is controlled, it can ensure the well-functioning of the metabolic processing, and the metabolism itself is producing the components that are being used by the genetic system. The metabolism is also producing all of the components for the membrane. And what you get out of this is a system that has all of the parts that it needs to maintain itself over time. The chematon has different functional parts, each playing different roles, but the roles are everything that all of the other parts need to play their roles. And so in some sense, the chematon sort of hangs together as a unified system, where every part supports and maintains the other parts so that the whole thing operates as one. The virus doesn't do this. The virus doesn't have a metabolism. The virus it has genetic code, but it doesn't have any processes to maintain itself in a homeostatic state. Maybe better than saying that the virus is not alive, to say something like it's inert, or it just sort of sits there until it hits the cell, in which case it activates and infects the cell. So this idea that the organism is alive because the parts support and maintain each other, this should be familiar from Aristotle's discussion of the functional parts of the soul. But in modern biology and systems biology today, they talk about this, the technical term for this is closure. So when the functional parts all support and maintain all the other parts so that the whole thing is sort of taken care of, this is closure. This idea comes from mathematics. In mathematics, in set theory, if you have a set of things and you can perform an operation on that set, and that every time you perform the operation, the result is another member of that same set, then you say that the set is closed under that operation. That anytime you perform that operation, you get back a member of the same set. So, for example, the even numbers are closed under addition. If you have any even number and you add it with any other even number, the result is another even number, right? So anytime you apply addition to the set of even numbers, you're going to stay within the set of even numbers. You get another even number. The odd numbers, however, are not closed under addition. If you have two odd numbers and you add them together, you're always going to get an even number. So performing the addition operation on the odd number set takes you out of the set, takes you to some different set, to the even number set. But performing the addition on the even numbers keeps you in the even number set. So even numbers are closed because in some sense they point to themselves. Any operation that you perform points to itself. And so when we talk about biological systems as being self-organized or as performing all the functions necessary to hold the whole cell together, we talk about this as biological closure. So biological closure is when the organism performs all the necessary functions to sustain and persist as a living thing. Again, no cell is entirely independent or isolated from its environment. Every cell requires an environment rich with nutrients in which it can expel waste into. And if you don't have nutrients in the environment, then the cell's not going to live. But granting a nutrient-rich environment, a system is closed when it's performing all the necessary functions in order to maintain and persist on its own. And so this is another way of saying that the virus is not alive. It's really to say that the virus is not closed. The virus does not contain within itself all of the necessary parts in order to maintain and persist as a virus. The virus just sits there until it degrades, and it needs to infect a cell, and the full cell has all of the parts necessary to reproduce and maintain itself, right? So a full cell is a closed system. It's a self-organizing, functionally coherent and whole system. But the virus, because the virus doesn't have these metabolic processes, the virus is not itself a closed system. Maybe the virus becomes a closed system once it infects the cell and gains access to all those other reproduction machinery or replication machinery. But the virus considered on its own, sort of the virus outside the cell, is not self-organizing, it's not metabolic, and so maybe it's not alive in the same way. It's not closed, so it's not alive in the same way. We'll see in a little bit when we talk about systems theory that maybe this notion of function, of self-organizing functions, will be a way of explaining teleology without an appeal to Aristotelian essences. Okay, so I've given an argument here that viruses are not alive. They're not alive because they're not metabolic, because they don't contain within themselves all the necessary machinery in order to reproduce themselves. I want to, again, caution that no organism contains all of the machinery that it needs. Every organism needs to be taking nutrients from its environment, needs to be spitting waste and heat back into the environment. So no organism is isolated from the environment. Every organism requires this complex dependency on its environment. But once that dependency is taken into account, the idea is that a self-organizing system is one that has all the rest of the parts that it needs. But how do you make this division really? I mean, you might think, and this is how modern biologists do think, that there really aren't the kind of strong categorical divisions in biology that someone like Aristotle thought there was. I mentioned this earlier, or maybe I mentioned this in class, but dogs and cats, we think of dogs and cats as different kinds of creatures. Dogs act in one way and cats act in another way. Maybe we know from personal experience that these stereotypes aren't always true, but we have these kind of intuitions or cultural prejudices that cats and dogs are just different kinds of things. But nowadays we know from biology that maybe cats and dogs today are different today, but not too long ago, within the last 50 million years, cats and dogs were the same kind of creature, and in fact were able to interbreed, and there was no difference between cats and dogs. And in fact, not only are cats and dogs the same if you go back far enough, but so are all the living creatures. Every single creature alive on the planet today is related in some distant way. We all share a common ancestor, right? So from the bacteria through the fish and the sharks and the fungus and the algae, reptiles and birds and mammals, all of us share a common ancestor at some point in the distant past. We have a closer common ancestor. So human beings are more closely related to the great apes. So we have a much more closely related ancestor to the chimpanzees than we do to the cats and dogs. But cats and dogs and human beings and chimpanzees were all mammals. And so all the mammals share a common ancestor in the not too distant past. And that mammal shares other common ancestors with the reptiles and the amphibians and so on, all the way back to the beginning of the planet. This diagram, I love this diagram. It's one of my favorite diagrams. The way this diagram works is that the start of the Earth is here at the center, 4 billion years or 4.5 billion years ago or so. And then as we get closer to the present, we sort of radiate out from the center. So these little concentric circles going out from the center to the present day. So the present day is here at the edge. The rim is all the creatures that are alive today. And you see there's a huge diversity today, much more diverse than there was in the past. Right? So there's less diversity in the past. This is something that evolution can explain. All these creatures alive today, because we all share a common ancestor and common evolutionary trajectory, that means that all these creatures that are alive today are also equally as evolved. Like we are just as highly evolved as birds, because both humans and birds alive today have spent the same number of generations and the same period of history evolving. Like it's taken the same amount of time from our last common ancestor to get to the birds as it has gotten to us humans. So birds are just as highly evolved. They're just evolved for a different niche, a different lifestyle, and same for all the other animals. Right? There are no big categorical distinctions between the different kinds of animals. We're all related. We all have common ancestors. And if you want to go back far enough, like we're all 50,000 generations related to dirt. If you go back 50,000 years ago, we are inanimate, organic, molecular operations on an early in the early primordial soup. And if this is how we're looking at the tree of life, if this tree of life is making us skeptical of the hard categorical distinctions between different kinds of creatures, then it might also be worth noting that viruses belong on the tree of life alongside all the other organisms. Viruses have DNA, and if you look at that DNA and how it relates to the DNA of all the other organisms, there's a place on that tree for viruses. In this image here, here are the bacteria and other organisms. I think these are the archaea. But these are a bunch of organisms. This is the tree of life. This is just another view of the tree of life. And one of the branches of the tree of life are all the viruses. Oh, I'm sorry. Down here are the eukaryotes. I'm sorry. Here are the bacteria. Here are the eukaryotes. And this is the proposed additional branch to the tree of life for the viruses. Viruses are a lot simpler than full organisms, but it's probably the case that viruses evolved after other organisms because you need the other organisms around for the viruses to reproduce and replicate. So our understanding of the relationship between the viruses and the other organisms is that viruses evolved later than more complicated organisms like bacteria. And so that's why the viruses here are on the eukaryote branch and not the bacterial branch, or sort of closer to the eukaryote branch. Here's another version of the same thing. Here, bacteria, archaea, and eukaryotes. And these are all the different viruses that we've sequenced and how those sequences fit in on a tree of life with the other organisms. And from this perspective, if we're looking at this from the perspective of the tree of life, then maybe the viruses are not such an anomaly, but that the viruses are organisms that are subject to the same kind of ecological and biological constraints that all the other organisms are also. Right? They're living in the same ecosystems. They're sharing our world with us. Maybe they're not metabolic, but they're certainly creatures that evolve and creatures with whom we share an evolutionary history. Not just that we have genetic relationships with them way back in the evolutionary past, but also that the way that we evolve is in reaction to and response to viruses that live all around us and on us and inside of us. So it's recognizing the active role that these viruses play in our own lives and evolution maybe will make us less hostile to thinking about viruses as part of the tree of life. Maybe viruses are part of life broadly construed, but they're just not metabolic parts of life. They're not engaging in metabolism on their own. Although viruses do engage in metabolism to some extent when they infect a cell, maybe this is a ship of thesis problem. Is it still the same cell when it's infected with a virus? Does that virus count as, does the infected cell count as an instance or an individual of the virus? Does the infected cell count as a different organism entirely from both of the other two? And maybe this is hard when thinking about viruses and individual cells, especially if you haven't thought a lot about the sort of fundamentals of biology. But this is a problem for us as well. Like human beings have all sorts of not just sort of biological subsystems, and sort of we can functionally break down a human being into different functional parts. But most of us isn't even human to begin with. So we have a thing that scientists are now calling the microbiome. The microbiome is all of the little organisms and bacterial cells and other kinds of organisms that live on and around and inside of us. These organisms are absolutely essential for your ability to, for instance, digest food. You could not digest the food that you digest. You couldn't drink milk, for instance, if you didn't have a bunch of bacteria in your stomach that can break down those proteins and help you digest them. And in fact, there are more non-human cells in your body than there are human cells. There are more let me say it one more time. There are more non-human cells in and around your things live on you and inside you. They evolve with you. There are some kinds of bacteria in your guts that only live in human digestive systems and don't live anywhere else. Um, um, these organisms are absolutely essential to your survival. If you take them away, you will die, just like if you took away your heart without replacing it with some artificial alternative. Right? If you were to take away all of your microbiome, if you take away all these non-human organisms that live on and around you, you would not be able to survive. So these organisms are absolutely essential to your survival. But again, they're not made of genes and DNA, right? The organisms that are essential to your survival as an individual organism are not on this branch right next to you, right next to the human. They're way over here in the bacteria section. Right, so they're distantly related to us genetically, but they're very deeply and intimately related to us in terms of our everyday operation. We wouldn't be able to operate on a daily basis without the existence of these organisms. So are they part of you? Is a human still a human without the microbiome? How do we talk about our identity and our persistence over time if, in fact, a big part of our constituents and a big essential function of our biological processes involves things that aren't human at all? Maybe I should mention that you can be identified uniquely by your microbiome. If I take a sample from your skin, and I don't even need to touch your skin, I can take a sample from the air around you. We all carry a little microbiome aura, a little pocket of air that sort of moves around with us as we walk around. And that pocket of air is distinct for every individual because we're all moving around in different spaces. And it's distinct enough that you can identify people uniquely. So there's experiments where they have a bunch of people have them walk around different places and come in, and then taking samples from just the air around them, not touching them, but just sort of grabbing a little sample of the air around them, and then going back and analyzing that sample, and being able to match up the samples with the person. So microbiome's incredibly important to who you are and how you're able to be alive. And maybe this is a challenge to this idea of closure. If closure is a thing, then maybe human beings genetically, if we take away the microbiome, are not a closed organism. And that maybe we only become a closed organism when we include a microbiome. And maybe the microbiome isn't enough. Maybe we also have to include our ecological frameworks and our environments. And so there's a question of, okay, so where do you bound the individual? This is a question that applies just the same way to the cell and to the virus as it does to the human organism. Like, where do you distinguish between the one organism and many organisms? These kinds of questions, thinking about the complexity of biological processes, is hopefully dissuades you from buying too much into these essentialist Aristotelian ideas. The essentialism doesn't really make any sense when you look at the biological details. The systems are too complex to be explained by simple essences or by vital force. The vital force theory is out. The teleological essentialism is rejected almost unanimously by science. If there's one thing that modern scientists agree about, it's that essentialist teleology doesn't work. It's not a good scientific theory. Right? And the idea is that this gets replaced with this reductive, law-like, deterministic Newtonian picture. But that's not really how we talked about the viruses here. Like, teleological essence don't work, vitalism doesn't work. And in fact, if you try to appeal to a vital force, you get this wrong picture of evolution. So maybe you want to appeal to something like self-organization or closure, but maybe that's too simple for explaining the tree of life, explaining things like viruses. That you really notice that the explanation of how the cell works is not about reducing it to the parts. In fact, I'm not reducing it to the atoms, to the fundamental particles that are being used in the cell. Instead, I'm breaking it down to this sort of high-level functional thing. What matters here is that the whole system is organized in this functional relationship with the different parts. So I've kind of been cheating when I tried to explain life as a self-organizing process, maybe that viruses are a part of. I've been cheating because I'm not using the sort of deductive, reductive, and deterministic framework of the Newtonian picture. Instead, I'm appealing to a different kind of view of mechanism. This is what I'm calling new mechanism. Not just me. This is what they sometimes call themselves the new mechanists. The point of the new mechanists is to give a mechanical theory, a theory that explains the operation of the parts, but that doesn't do it in a reductive way. So the new mechanist. So the contrast here is between the classical mechanists and the new mechanists. The classical mechanists are reductive and deterministic, whereas the new mechanists are non-reductive. They're systems theoretic. They want to talk about the organization of systems and how that impacts the behavior of the whole. So the mechanist that I like here is Bill Bechtel. Bechtel has a bunch of articles in the readings that you should read. This is an image that's actually not from Bechtel, but it's from the mechanical, the new mechanisms in science article in the SEP. And this is a quote from Bechtel that's quoted in this SEP article right next to this diagram. But Bechtel defines a mechanism. What a mechanism is a structure performing some function in virtue of its component parts, component operations, and their organization. The orchestrated functioning of the mechanism is responsible for one or more phenomena. So the idea is that we appeal to mechanisms to explain some phenomena. Right? So some behavior or property is the phenomena that we're wanting to explain. This is the phenomena, and the idea is that we explain the phenomena mechanically when we explain it in terms of the parts, their interactions, and their organization, right? So how the different parts interact with each other and how the whole system is organized. And mechanical explanation is an explanation of phenomena in terms of these parts, their operations, and their organization. The important thing here is the organization, is that we're not just talking about the parts understood simply in terms of universal laws. Instead, we're talking about the parts in their arrangement with each other and how those operations impact both the operations of other components, but also the operation of the whole. So new mechanists are non-reductive. They recognize that there is a whole. Right? So the whole point of the Newtonian mechanics is that we're reducing everything to its simplest parts and the law-like operations that operate on those parts. But the new mechanists are non-reductive. You don't reduce everything to the simple parts. Instead, you recognize that some things emerge as complex organized properties, and you explain those emergent properties in terms of the organization of lower level parts. And the organization here is precisely the non-reductive word. The organization is not just the parts, but it's also their relationship to each other, how they interact with each other. In other words, you might think that the new mechanists want to have it both ways. They both want the precision and predictability of Newtonian classical mechanics. They want the Newtonian mechanics that gets rid of teleology and vital forces and other sort of weird immaterial operations. But the systems theorists also want to recognize that organization results in functional structure, and that because of functional structure, certain high-level properties emerge. So for the systems, I'm going to go all the way back. So for the Aristotelian, an agent is a living creature, and living creatures are just a fundamental kind of thing. You can't really explain that kind of thing in terms of simpler parts. Instead, what you explain is the formal cause, the form, the animating principle, and you explain in terms of the goal or the trajectory or sort of what it's for. Right. So you're not reducing things to simple parts. You're explaining things in terms of these of what can be potentially actualized in this teleological sort of forward-looking way. Okay, so Aristotle has teleology to explain the future, and you don't reduce to simple parts. In the Newtonian picture, you reduce to the very simple parts, and you have these universal laws that explain how the system evolves. And from the Newtonian picture, there are no final purposes, there are no goals, there are no meanings. All of that stuff is just an interpretive conceit. Instead, it's just atoms in the void operating in particular ways. The systems theorists wants it both ways. They want the predictability of the Newtonian framework, but they also want the ability to talk about emergent organizing processes, higher order processes that emerge from lower order mechanisms. So a systems theorist is going to say something like life is a higher order phenomena that emerges from the organization of lower level parts. Part of these organizational parts might involve things like metabolism, right? And so it's because of the metabolic structure of these chemical pathways that you have this higher order property like life. Right? The idea here is that you're not saying that life doesn't exist. You're not saying that there are no higher order properties like the Newtonian. You're also not explaining the higher order properties in terms of some vital force or some non-material thing. No, there's no vital force. There's no elan vital. There's no vital spirit that explains the higher order properties. There's no essence. Instead, there's just these mechanical operations that are operating at a lower level. And when you get those mechanical operations organized in the right way, hooked up with each other in the right way, so that they're all maintaining and supporting each other, then you can get these higher order emergent properties. So life on this view is an emergent property. It emerges from self-organizing metabolic processes. The idea is that this systems theoretic view, this more complicated view, where you're discussing things in terms of the emergent of higher order properties, that you need this kind of view to explain anything that can't be explained by simple Newtonian mechanics. That includes things like population dynamics and evolutionary biology. Darwinian theory doesn't really work on a purely Newtonian system, but it works just fine on this sort of complex theory, emergent phenomena framework. Statistical mechanics and thermodynamics, how heat radiates from a hot body to a cold body. This is not something that the law of gravity explains very well. In fact, we discovered in the 1800s that in order to explain heat and how heat transfers and thermodynamics generally, you need to think about things not in terms of reductive properties and simple parts, but you need to be thinking about things in terms of ensembles. Right, so this is why the science of heat is statistical mechanics. Right? Thermodynamics is studied in terms of statistical mechanics, in terms of thinking about ensemble states and lots of properties. Like you think about a gas in a box and how that gas flows from one side to the other. Here you're not thinking just about the individual particles of gas, but you're thinking about how big collections of gas interact with each other. And this requires a non-reductive view, statistical mechanics. You might think of statistical mechanics as this kind of non-reductive view. Another thing that gets developed in this more recent time period is something like quantum mechanics. Quantum mechanics is non-deterministic. In the Newtonian picture, future states follow necessarily from past states. But nowadays, we believe that the world is probabilistic. It's not deterministic, but that there's some probabilities, there's some chance of things happening or not happening. Like this quantum mechanics is a way of building rules around these probabilities, around how these probabilities impact each other. Not just probabilities. In quantum mechanics, they call them amplitudes because they're complex numbers. So there's a little bit of technical machinery in order to mess around with these probabilities. And quantum mechanics is just the science of how these probabilities affect motion. So quantum mechanics is not a deterministic science. This is another maybe reason for rejecting the Newtonian framework. Nevertheless, quantum mechanics is a mechanical framework. So you don't need to be a deterministic framework in order to be mechanical. Quantum mechanics is mechanical, but it's also probabilistic. There's probabilities of things happening or not happening. And we can talk about those probabilities in law-like ways. So, for instance, if I have a dice, like a six-sided die, and I roll the die, if it's a fair die, it should land on each side 1 out of 6 times. But I can make mechanical adjustments to the die to change the probability distribution of how it lands, right? So if I take one side of the dice and rub it on sandpaper and sort of grind off one side so that that side is shorter than all the other sides, that's going to affect how the dice rolls. This is how you fix the dice. That means that one side is going to be shorter than the other sides, and that is going to affect how it lands. And so maybe the dice before was a fair dice and every side had a 1 out of 6 chance. But maybe after manipulating the dice and rubbing one side off, now the dice is weighted and it will land on some more than the other. Right. So here, this is a mechanical operation that changes the probabilistic character of the system. Right. So probabilities and mechanisms are perfectly compatible. Quantum mechanics is an example of a probabilistic mechanical theory. There's nothing about mechanisms that requires it to be deterministic. So systems theory is the non-deterministic, non-reductive mechanical theory. And this is maybe to some extent how a lot of the sciences operate today, especially things like systems biology. And I want to say that computational complexity is also a field for systems theory, complexity theory generally. That in order to understand how computers work, you can't just be working in the old Newtonian framework. You have to be working in a much more complicated and sophisticated system. On the new mechanistic framework, you can recover a sense of function and control, organization, and so in some sense a kind of purpose, not a grand purpose like God designed it for some reason, but rather just a purpose relative to the other parts of the system, right? So the heart evolves to have its function over many generations, over thousands of generations, over millions of years, because of the way that that part interacts with all the other parts, because of the way that evolution puts certain pressure on the development of some behaviors and so on. Right? So having this sort of systems theoretic view, having this long evolutionary view, allows us to explain things like how biological systems have functions. It also lets us talk about control more generally. Let me pull my head out of the way. So the science, maybe the archetypical science or the sort of prototypical science of the modern mechanistic views in ways that contrast with the Newtonian mechanics. The poster boy for new mechanistic theories is cybernetics. Cybernetics is part of the control theory that goes into things like robotics today. Anything that has like hydraulics on it to move around is using theories that are developed from cybernetics. The word cybernetics comes from the Greek word kubernetes, which means to steer or govern. Kubernetes, like the captain of steers a ship. Kubernetes is what the captain does to the ship. The captain steers the ship, guides the ship, controls the ship. And so cybernetics is the study of control in this sense, the theory of control, theory of regulation. How do you keep a system in some state? So we've already been talking about this a little bit. We've been talking about how to keep a cell in a certain state, keep a cell in homeostasis, or keep a virus in a state where it can replicate. But this kind of control extends more generally, and this is generally what we're thinking about when we're thinking about mechanical systems that are controlled. So a control system, a system exerts control when it has direct influence over the parameter of some system. Maybe the best example of this is a thermostat. So I have a thermostat. You might have heard my air conditioner going on and off over the course of this video. And it's going on and off because it's controlled by a thermostat. Right? There's a thermometer inside the air conditioner that's sensing the temperature in the room. I've set the air conditioner to keep the room at say 72 degrees. And so that's it's so the air conditioner is a control system. It's controlling the temperature in the room. The temperature in the room is a parameter that's controlling, and it can adjust the temperature up and down. If it turns on, if the air conditioner turns on, then that's going to lower the air temperature. But once it turns off, the temperature is going to raise. And so the way that the thermometer works is that when the temperature gets too high, the air conditioner turns on and lowers the temperature to a desirable point, and then it turns off, and then the temperature rises again, and then the air conditioner turns back on and lowers it. And so the temperature in the room goes up and down in this controlled fashion because of the operation of the air conditioner. In order to achieve this control, you need a couple of things. You need, first of all, a sensor. so that you can tell what temperature it is. You can imagine an air conditioner without a sensor that just keeps blasting air. It just keeps blasting air until you turn it off. In this case, there's no sensor, and so there's no feedback, and so there's no control. So in order to have control, you need a sensor, and that sensor has to be effective at changing the behavior of the thing. So the other thing that the air conditioner has is an effector, and the effector is its ability to change the thing. So in this case, the air conditioner's effector allows it to cool down its surrounding environment, and so it cools. So it deploys its effector. It cools the environment, and then it senses what happens. And if it achieves the desirable states, then the air conditioner turns off. But it keeps sensing, and then once the temperature goes past that desirable state, then it turns the air conditioner back on. And in this way, the air conditioner controls the room temperature. So this is control. This is not consciousness. I'm not saying that the air conditioner is conscious or that it has a mind or that it's thinking about anything. I'm just saying that it has control. It's basing that control on sensors. So it's sensing from its environment, and it's using these sensations in order to adjust its behavior. So there's this kind of control feedback loop. That said, the feedback loop here is pretty simple, and you can build something that executes this feedback loop from very simple materials. An air conditioner. Nowadays, air conditioners are mostly controlled by digital thermostats, but it used to be the case that air conditioners and heating systems were controlled by mechanical thermostats designed around a bimetallic strip. So you can get the control system in this feedback loop to be as simple as just a piece of metal, or two pieces of metal. So it's a bimetallic strip. So it's a strip of metal. It's two pieces of metal that are glued together tightly, and the idea is that they're two different pieces of metal, and made of different kinds of metal. So like one's copper and one's steel or whatever. The idea is that because they're different kinds of metal, because they have different in particular, they have different thermal properties. Metal expands when it gets hot and contracts when it gets cold. But because they're different kinds of metals, one will expand faster than the other. And because one expands faster than the other, that'll make it bend, right? Because one gets longer and the other doesn't get as long. So that means it bends one way or the other. And just having the metal bend one way when it gets too hot, and if you put an electrical contact on that, you can let the little metallic strip close a circuit. And so just from the metal bending back and forth from fluctuations in the ambient temperature is enough to get the air conditioner to turn on and to close that feedback loop and get a system that can control the air. There are other kinds of controllers or control loops. Maybe a famous one here is the Watt's governor. So this is a control system for a steam engine. Here's a little steam engine. The steam engine produces heat. And if you keep letting it produce heat, then it might overheat or might blow out and damage the engine. And so what you want to do is make sure the temperature stays in a certain range. And what they have here, the Watt governor, is this little spinning thing with balls. And the idea is that the thing with balls is on little hinges. And when it spins faster, the hinges go out, and that raises the governor up. And the governor's on top of a little vent release system. So when the engine's burning really hot, then the governor spins faster. And when the governor spins faster, those balls move the hinges out. And so the whole governor raises a little bit. And because it's attached to the vent, when it raises, it also vents the steam. And when it vents the steam, that means the engine cools down. And when the engine cools down, that means it spins slightly less fast, and that means the plug falls back down and it closes off the steam, right? And then if it's closing off the steam, then it's getting hotter inside, and so the engine spins hotter. And the effect is that this little governor, just by spinning around, is able to keep the steam engine operating within a certain temperature range. This is very important for making sure that it's reliable and safe and so on. So this little governor, it's a dynamical system. This is a little bit more complicated than the bimetallic strip, but these are both control systems. Again, control here is not about intelligence. It's not about any kind of cognitive activity. It's really just about the ability to have influence over certain parameters of the system. But the idea is that you are also just a very complicated control system. So I'm going to argue, especially next time when we talk about the mind, that you are a machine, that you're a robot, and eventually I'm going to argue that you're a computer. And part of the argument here to say that you're a machine is not to say that all of your behavior can be explained simply in terms of your atoms. So that's not the point. The point here is to say that you're a complicated mechanism. In fact, you're lots of complicated mechanisms, and those mechanisms all hook into the other mechanisms in ways that allow for the full range of behavior that you have. Maybe an easy way of seeing the same feedback loop that we saw in the air conditioner. You have that almost exact same feedback loop in your body. It's just a much more complicated loop, but same basic structure where you have sensations, where you sense things in your environment. You have perceptions of your environment. So your environment, here's you, the organism. You sense things in your environment, and then you process those sensations in order to change your behavior. And your behavior results in another change to the environment, and then you can sense that change to the environment again. So just in the same way that the air conditioner is changing the temperature and then seeing the results of that change and then using that to adjust its own behavior, and this is exactly what your brain's doing. You have in your brain this little blue line right here in the sort of mid part of your brain, right in the center of your brain here. This is the primary sensory cortex. Your sensations from your eyes and all the other sensory apparatus is going through this part of the cortex. And this part of the cortex hooks up with your primary motor cortex, which is what controls your behavior and your bodily operations. And there's this big feedback loop that goes through your body so that you sense things, things that you sense make you change your behavior. Your changes in behavior have an impact on the environment, and then you sense that change in the environment again. And this is this big perceptual feedback loop that's responsible for your actions and behaviors, at least your cognitive actions and behaviors as a result of the sensation of your sensations, right? So this is the sense in which you're a machine. You're not a machine because you're made out of metal parts. You're not a machine because someone programmed you or designed you. You're not a machine because everything about you is physical, although that's true. But you're a machine in the sense that explaining your behavior is about explaining the operation, the parts and how they interact with each other, and how they're organized in a way that results in the emergent behavior of the whole, right? So understanding this perceptual feedback loop from sensory inputs through motor outputs is one of these feedback loops, these mechanical feedback loops that explains your behavior. Of course, this doesn't explain all your behavior. There's a lot of processes that are automatic in the body, the sort of autonomic nervous system. And so like things like digestion and even things like maintaining your balance over time. Some of the stuff is done through your perceptual feedback loops, but some of the stuff is done without any awareness at all in your body. And these perceptual systems are only some of the complex feedback and control mechanisms. Like you have another entire mechanism in your body, a whole system in your body for maintaining your internal temperature. Your internal temperature, 98.6 degrees is like an average temperature for people. People are sometimes higher and sometimes lower than that. But 98.6 degrees is very often far outside of the temperature of the ambient environment. The ambient environment might be 60 degrees outside, but your body stays 90 degrees. And in order to maintain that temperature, your body has all sorts of feedback processes for burning energy and keeping the heat up in order to maintain your core temperature so your organs don't fail. If your body temperature drops to 60 degrees or lower, you'd be in real trouble. But your body has all sorts of complex mechanisms that sense the situation and make fine adjustments to your behavior so that you can maintain an internal temperature. For instance, right now I'm kind of sweaty. Even though the air conditioner is going on, I'm sitting in front of a bunch of lights and I've been talking at the camera for a few hours, and this has made me a little bit sweaty. And sweat is my body's natural process for trying to maintain bodily temperature. When you sweat and the sweat evaporates, that cools off your skin a little bit, and this helps you maintain temperature. Right. So me sweating is my body adjusting to changes in environmental temperature, changes in my own body temperature in order to keep myself within a certain temperature range. In the same way that the air conditioner is trying to maintain a temperature range in the room, my body also has a bunch of mechanisms for maintaining temperature, the body's temperature. So you're a machine. You're a complex machine with emergent properties. So you're not a machine in the reductive deterministic sense. And we have to deal with that reductive deterministic sense because the way that Newtonian mechanics thinks about the world is not the way that we should be thinking about the world. The world is not deterministic. It's not best explained in these reductive terms. Right? So I already talked a little bit about quantum mechanics as being probabilistic. And I want to emphasize one more time that just because quantum mechanics is probabilistic doesn't mean that you can't explain things or that things don't have an explanation. In fact, quantum mechanics is one of the most successful scientific theories we've ever built, and it can make predictions that are more accurate than any scientific theory we've ever constructed. Some of the predictions of quantum mechanics agree with observation to one part in a trillion. These are some of the most precise and accurate theories that we have in science. This 1 part in a trillion is the magnetic moment of the anomalous magnetic moment of the electron. So there's a property of the electron, is magnetic moment. It has to do with how the electron spins. And we have a theory for predicting what that value should be, and then we can actually observe it in an independent way in our laboratories. And the theory agrees with the prediction to very, very high resolution. We're very confident that our theories are right. Our quantum field theory really is the best theory that we have in science, and it explains the operation of just about everything in the world. The things that quantum field theory can't explain are things that are very extreme parts of science that we really don't interact with on a daily basis. So quantum field theory doesn't explain dark matter. It doesn't explain dark energy. It doesn't explain neutrino oscillations. These are things that scientists know happen and that we know that our theory doesn't account for. So we know the theory isn't complete. It's not. We don't have a complete physical theory. But the theory is complete for just about everything outside of those ranges. Neutrino oscillations are with these very, very light particles moving at the speed of light. Dark matter is about how galaxies rotate, and it's really something that only impacts at the scale of galaxies and galaxy clusters. But on the scale of planets and stars, dark matter really doesn't have any impact on our daily lives. Same thing with dark energy. Dark energy is about the expansion of the universe, the rate of expansion over time. It has something to do with the cosmological constant. But this is not something that affects our everyday life. In terms of everyday observations, in terms of the kinds of things that you might interact with or see as a human being living close to the surface of the planet, quantum field theory explains every operation, every interaction that you see. So it's true that the theory has randomness built in, but that randomness is extremely explanatory, and that we can make very high accuracy predictions, extremely precise predictions, using this kind of theory. So the world has probabilistic elements to it. Not everyone agrees with this. There are some people who think the world is still entirely deterministic, but the most popular physics theories think that quantum mechanics describes how the world works, that the world is in some sense random. Nevertheless, it's predictable in this mechanical way. Here's another problem: that the world is chaotic, and chaos is not just randomness. Chaos has to do with predictability. Has to do with predictability in deterministic systems. So my favorite example of chaos is Plinko. Y'all might have played Plinko before or watched Plinko on. They had these kind of games at the fair, and it was on Price is Right for a long time. So Plinko, you have this little disc, and then there's this board, and the board has a bunch of little pegs in it, and the disc bounces on the pegs, and then it falls in some slot at the bottom of the board. And this is a chaotic process. You can drop that disc in one space, and it'll fall down and land in some slot. And then you can drop the disc in what's basically the exact same space, and it might drop in a completely different spot. It's really hard to predict because it's chaotic, and what that means is that it bounces around in ways that are difficult to anticipate. Notice here, it dropped in the 10,000, but he let go of the disc at the top of the Plinko board in some completely different place, but it happened back into that 10,000 slot. And the reason that this is chaotic is that very minor deviations in where you put the disc, very small, maybe even imperceptibly small differences in where you place the disc to begin with, is going to end up having really big consequences for what happens to the disc as it goes through. This is what chaos theory calls the butterfly effect. The butterfly effect you might know from movies and popular culture. The butterfly effect is when small changes to the initial conditions of a system end up having very large changes to how the system plays out over time. So the idea is that The butterfly. So the butterfly effect is a butterfly flapping its wings on one part of the world causes a hurricane on the other side of the planet. And again, the idea is that the butterfly flapping its wings or not, these are very small changes, very minuscule changes that you might not even notice if you're looking around. But those very, very small changes can end up having a huge impact, right? The difference between a butterfly flapping its wings or not is small, but the difference between a hurricane or not is huge, like billions of dollars of damage, potentially. So the idea that there's some relationship between this very small effect and this very huge effect is what chaos theory is all about. In Aristotle's time, he would have denied that this kind of thing is possible, that maybe there needs to be something comparable in the cause and the effect. In fact, a lot of people argued exactly this way, that there has to be some similarity in the cause and effect for there to have this causal relationship. And chaos theory is supposed to sort of throw that into question, that something that's very small can have an effect that's very large. And it's because some systems are very sensitive to initial conditions and change dramatically depending on very small changes to those initial conditions. I want to go through sort of 2 demos of this, and this is what I'm going to end the class with. The first demo I want to give is let me see if this works. No, it doesn't work. I'm going to need to add this source. So, okay, so I'm in my browser. So the first thing I want to talk about is the logistic map. There's actually a really good video that I'll put in the reading list about the logistic map. So this is the first example that I want to go through of chaos, just to get your appetite whet, and then I want to show you maybe a more compelling example with the game of life. So the logistic map is a sort of traditional equation for thinking about dynamical systems. It's a very simple, nonlinear dynamical system where chaos arises in a very clear way. So it's a dynamical system. Dynamical system here just means that it changes over time. And in fact, what you see is that the system is indexed to time. So the n, you can think of n, x to the n. That n tells you the time step that we're on. And so what the equation says here is that to figure out what happens in the next time step, in n plus 1, x sub n plus 1, the value of x sub n plus 1 is equal to the value of x sub n. So the next time step is equal to this time step times 1 minus this time step. So x sub n times 1 minus x sub n. And then that quantity times r. So r, the parameter r, or sometimes is omega. This is called the growth rate, something called the growth rate, or the how fast the model grows. This logistic map is often used to model things like reproduction, right? So the idea is that how many organisms will you have in the next generation? Well, the number of organisms in the next generation is going to be the number of organisms in this generation times 1 minus the number of organisms in this generation times the growth rate, how fast these organisms are growing. And so the eventual result is going to depend heavily on the growth rate, and it's also going to depend on what point in this process we're at. So this is a dynamical system. It depends on the state, the n that we're at. The equation here has this recursive structure. So we want to pick some starting point. And then once we pick a starting point and we pick a value of r, then we can start plugging in the equation and sort of churn through the equation and see how it develops over time. I actually have an example of this in the complexity book. This is Melanie Mitchell's complexity book. This is one of the books in the reading list. This is actually just like an introduction to complexity theory, but it goes through some of these examples in some detail, and it goes through the logistic map in some detail. Let me actually go down here. I'm going to go back to the Wikipedia page in a second because there's a nice little graphic for that. But sorry, the book talks about Aristotle a little bit too, but it also talks about population growth and growth, and it gives the example of the logistic map. Here we go. Okay, so we went through the equation. Here's the equation again. the value at the next step is equal to r times the value at the current step times 1 minus the value at the current step. So again, you need to pick your values. You need to pick a value for r, and you also need to pick a starting value at x sub 0. So, and you can plug this into a calculator. You can follow along with yourself. So the first one Melanie Mitchell picks as an example to work through is where this will get a little bit mathy, but it won't take too long. So the first value they pick is r is equal to 2. And for the value of the starting position for x, it has to be some number between 0 and 1. So she picks 0.5, just halfway through. So 0.5 is the starting value, and r is 2. So we can actually come up here and plug it in ourselves. So if the starting value is 0.5, then we have so then the next value is going to be 0.5 times 1 minus 0.5. And 1 minus 0.5 is also 0.5. So 0.5 times 0.5 is 0.25. And then the value for r is 2. So 2 times 0.25 is 0.5 again. So remember, the starting position for x is 0.5. But when we plug it into this equation with r value equal 2, we get 0.5 as the result. And the idea is that we plug this result back into the equation, but if we plug 0.5 back into the equation, we get 0.5 again. So 0.5 as a starting position and 2 as r is a fixed point. It doesn't go anywhere. It stays at the same value. R stays at the same value, right? So as she says, thus if r is equal to 2 and the population starts off at half the maximum size, it stays at that size forever. It stays at 0.5. The population size stays at 0.5 forever. What happens if we change it? So in this case, we're going to keep r at 0.2. We're going to keep r at 2. We're not going to change r, but we are going to change the starting value. So instead of starting at 0.5, half the capacity, the maximum capacity, population capacity, instead we're going to start at 0.2. So if we start at 0.2, and again, we plug it into that equation, you can see 0.2 times 1 minus 0.2, which is 0.8. So 0.2 times 0.8 is 0.16. And then 2 times 0.16 should be 0.32. So if we start off at 0.2, then the next value we get is 0.32. If we plug 0.32 back into the equation, we get 0.4352. If we 0.4352 back into the equation, keeping r fixed at 2, then we get the sequence of numbers, and you can see that the numbers grow until they hit 0.49, and then 0.499, and then 5. But we know from the first example that if it hits 0.5, it'll just stay at 0.5. So in other words, we get, if we start off at 0.2, 0.2 grows until it hits 0.5, and then it stays at 0.5. This kind of growth rate is called a fixed growth. I'm sorry. This is called a fixed attractor. So 0.5 is an attractor for this dynamical system because once you're at 0.5, you stay at 0.5. And what's interesting is that nearby values grow to 0.5, and then once you're at 0.5, you stay at 0.5. So if we start off at 0.2, the values grow to 0.5, and then they stay at 0.5. Notice it grows pretty quickly and then sort of levels off, and then it hits 0.5 and keeps going. We can do this with other values. Plug in a different value. Here they're plugging, so we're still staying at r is equal to 2, so we haven't adjusted the growth rate yet. But here we're starting off at 0.99 as our initial population. So the population starts at 0.99. If you plug it into that equation, you'll see that it drops off really quickly because it's 0.99 times 1 minus 0.99, which is 0.01. And that's going to make a very small number as your next step. But that small number eventually grows, and in fact, it eventually grows to 5. And in fact, any starting value you pick between 1 and 0 will eventually grow to hit 5 and then stay at 5. 5 is a fixed attractor for r equals 2. No matter what value you put in for the starting position, the value will grow until it hits 5 and then stay there. So 0.5 is a fixed attractor for this system when r equals 2. So we tried different starting values, and we find that it doesn't matter what the starting value is. When r is equal to 2, it grows to 0.5 and stays there. But we can pick other values for r. So here's an instance where we pick a slightly bigger value for r. And again, you can plug in the equations. It doesn't matter where you start. Here they're starting at 0.2. But if we start at 0.2 and we have r as 3.1, so a slightly higher value for r, slightly higher growth rate. But But that doesn't just mean it grows on forever. What happens in this case is that the population grows to about 0.8, but then it falls back down to 0.5, and then it grows back again to about 0.8 and falls back down to 0.5. And in fact, if you plot this graph, you see that it oscillates between these two possibilities. What you have here is not a system that grows to just one fixed value, but it grows to oscillate between two fixed values. So you have a system that moves back and forth. So we call this an oscillating attractor. This is not a fixed point attractor where it goes to one value, but this is an oscillating attractor where the system develops so that it moves back and forth between two different states. It's an oscillating attractor, but we can get even weirder behavior if we make R slightly higher. This is 0.49. We can see that it's oscillating, but here it's not oscillating just between two values, but it's actually oscillating between four different values. It's going back and forth between these four values in this rather odd pattern, but it still is an oscillating attractor. It's just a more complicated oscillating attractor. But once we put R over 0.5, we get wildness. We get systems that behave very, very differently. And for R over 3.5, the logistic map is chaotic. And you can see exactly what that means in this graph right here. So this is two different trajectories of the logistic map. So this is two different graphs of the logistic map, two different sort of runs of the logistic map with two different starting points. So these are both in the chaotic regime with R is equal to 4, but we've chosen two different starting points. For one of these, we've chosen the starting point at 0.2, and for the other one, we started the starting point at 0.20000000001. These two values are very, very similar. They're only off by a very small number, and in fact, that number is so small that it might be below our measuring instruments. Like we might not have measuring instruments that are sensitive enough to detect the difference between 0.2 and 0.2000001. So it might be, for all intents and purposes, that these two values are the same for us because we can't tell the difference. We don't have measuring equipment sensitive enough to the difference to tell the difference. And in fact, if you plug these two values into the logistic map, you actually get basically the same results for the first 40 states in this 20 states or 40 states. 30 or so iterations. Between 20 and 40 is 30. So for the first 30 states, these two initial states come back with the same value at R equals 4. It looks like these are basically the same equation for 40 iterations of the logistic map, or for 30 iterations of the logistic map. Once you get over 30 iterations, though, the two equations start to come apart, and you can see this here. So there's actually two equations here. One of them is with nodes that are dark, the dark black nodes, and the other ones are nodes which are the open circles. So the dark black nodes and the open circles are values of the logistic map, and you can see that they're slowly starting to come apart. That early on in the logistic map, they have the exact same value, but as we keep going, these values start to come apart till when we get to like 60 or 80 iterations, the two values are just completely different. Here's one equation with these values, and here's the other equation with this set of values up here. It's just a completely different set of values. This is the butterfly effect. This is a mathematical version of the butterfly effect, where the butterfly effect, what chaos is here is just extreme sensitivity to initial conditions, right? The difference between these two starting states is very, very small, maybe below our capacity to sense it, maybe the difference of a butterfly flapping its wings or not. And you might think that that small difference won't matter at all, but in fact, this equation, even though the equation is very simple, the equation is complex enough that these two, this difference in starting position is enough to make very dramatic differences, just 60 or 80 steps into the equation. And this diversion is what's characteristic of the logistic map. So let me just go back to the Wikipedia page. So the Wikipedia page has a map of this diversion, how these equations diverge, and how much divergence you get for different values of R. So these are the values of R. So you can see that you get almost no divergence for the first, for R equal to 1. You start to get these oscillating attractors for R up to 3. And then you get even more. You remember we saw the oscillating, but it was oscillating between like 4 different spots. Well, that's what's happening up here at 3.5. But then once we get up into 4, there's so many different variations in the logistic map that it's chaotic. You can't tell where you are or where you came from. And this is best represented in this image here. So this is still the logistic map. This is just another way of representing the logistic map. Here on the left, we're slowly increasing parameter R, and starting from 0.2. And you can see, actually, let me refresh this so we see at the beginning. So at the beginning, we know that that 0.5 is a fixed point for the logistic map. So it starts off at 0.5, but as we slowly increase the growth rate, we see that the equation gets more and more complicated, eventually introducing this oscillating pattern. So when we're over 3, we have a clear oscillating pattern. And then as we get closer to 3.5, the oscillations are going to get wild. But then once we pass 3.5, we get into the chaotic regime. And this is what the equation looks like as we increment the growth rate just by very slight amounts. You can see that the equation just starts going all over the place. That kind of, it looks like random behavior. It's not random, though. It's entirely deterministic from that equation. If you know the starting point, then you can you can compute what every state afterwards will be. There's nothing random about the logistic map at all. Once you choose your starting position and you choose a value of R, everything that happens to the equation is entirely determined. Nevertheless, despite a deterministic framework, this is still chaotic. It's chaotic because small variations to those initial conditions can cause large changes into how the overall system behaves. This is part of what we didn't get in Aristotle, is this appreciation of complexity, of chaos and complexity. So not only do we not get this in Aristotle, but we don't get this by the early Newtonians either. The Newtonians think, like Laplace, that if you know the starting state of the world, if you know what state the world is in, and you know the laws that govern the world, then you can predict everything that happens in the future. That the world is entirely deterministic. But we know from chaos theory that even if the world were entirely deterministic, and we know that the world is not entirely deterministic because of quantum mechanics, there's probabilities involved. But even if we ignore those probabilities in the quantum level, and we think about the world as entirely deterministic, even still we couldn't predict everything that's going to happen because chaos rules. So if we're off by even just a small amount in our models, then the predictions that our models generate is going to differ from what actually happens by arbitrary amounts. And the amount that your model differs might be so small that you can't test that amount, you can't detect that difference. In which case, your models are going to start to fail, and there's really nothing you can do about it. It's not because the world is random. Oops. It's not because the world is random. I'm sorry, I was on this slide. Right, this is the Laplacian slide where everything that happens in the future is determined by everything that happens in the past. And chaos works in this kind of deterministic framework, and that even in a deterministic framework, you can't predict everything that's going to happen because chaos means that small variations will throw off your predictions in arbitrary ways. So the Newtonian classical mechanics hope, the dream, that you can predict everything that happens in the future, that you can generate a set of mechanical laws that predicts everything that's going to happen. This is just, it's a dream, it's a fantasy. You can't do it for any sufficiently complex system. You're not going to get perfect predictions. It's not because the models are bad, it's because of chaos. It's because you can't build, in some sense, you can't build good models. But once you understand that this kind of chaos can exist within deterministic frameworks, once you understand that mechanical systems can be random and chaotic in exactly these ways, then the prospect of explaining how something like the emergent features of life, that explanation doesn't seem so hard anymore. And I want to give an example of this using the game of life. So back to the browser. Sorry. Get myself out of the way here. again. Okay. So this is Conway's game of life. Here we go. So this is Conway's game of life. You might have seen this before in a computer science class. It's very common for introducing computer science. Conway's game of life takes place on a big grid of cells, and each cell in the grid can be either on or off. So the white cells here are off, and the black cells are on. And the idea is that you just have this big grid of on and off cells, and the cells turn on and off by a set of rules. But the rules are supposed to be very simple, and these rules are also modeled on population dynamics and biology. So there's a rule that kills a cell for underpopulation. There's a rule that kills a cell for overpopulation. There's a rule for reproduction, and there's a rule for sort of homeostatic, just stay as you are. So here are the rules. Any cell with fewer than 2 live neighbors dies as if by underpopulation. So let's go back down to the grid really quickly. So you can see that it's a straightforward grid, and the neighbors are the neighbors that are in the the neighbors are anyone around it, including the diagonals. Yes, the diagonals are also count as part of the neighbors. So any one of the cells, so if we're thinking about this black cell as a cell that we're considering, then its neighbors include all of the cells around it in a square, including the diagonals. Okay, so these rules are about whether one cell stays alive or not, whether we turn the cell on or off. And the way that the game of life works is that you just apply these rules to every single square on the board. And then that gives you the next state. And then you apply the rules to every single square on the board again, and that gives you the next state. And you keep doing this to get the states as they develop. So again, the rules are, if the cell has fewer than 2 live neighbors, then it dies as if by underpopulation. So if fewer than 2 of its neighbors are alive, it dies. Also, if more than 3 of its neighbors are alive, it dies. If it's overpopulated, if there's more than 3, it dies. If there's fewer than 2, it dies. But if there's exactly 2 or 3 live neighbors, it lives on to the next generation. So the way that you get a cell that's on to stay on is by having 2 or 3 of its live neighbors, 2 or 3 of its neighbors alive, and then that cell will stay alive. You can also have a cell that's off turn on. This is reproduction. So if the cell has exactly 3 live neighbors, then it turns on, becomes a live cell, as if by reproduction. And that's it. These are all of the rules. Everything that happens in the game of life is a direct product of these 4 rules. Notice that these rules aren't entirely reductive. You can't determine what happens to a cell by just thinking about the properties of the cell. You have to think about the way that cell relates to things around it. So there's this organizational structure to it. And what's really interesting about these, so it's very simple rules, but the rules are enough to give you very complicated behavior. So let me introduce you some of the simple processes in the game of life. And let's first focus on the still lifes. So we can see, so these are still lifes. They're still lifes in the sense that they don't change over time. If you have a still life and there's nothing around that still life, then the next state you'll still have that still life. And we can use this to sort of test the rules and see how the rules work. So remember, if you have between 2 and 3 live neighbors, you stay alive. So each one of these squares in the block has between 2 and 3 live neighbors. This square is touching these 3 squares, and every other square is touching 3 live neighbors. Every square is only touching 3 live neighbors. They're not touching 4 live. There's no square that's touching 4 live neighbors. Every one of the off squares is only touching 2 live neighbors at most. So these, so like this square is touching these 2 live neighbors, but it needs to be touching 3 live neighbors in order to turn on. And none of the outside squares are doing that. So the still life just stays a still life. If you apply all 4 rules to every square in this box, then you keep those squares. Nothing changes. Same thing with the beehive. Beehive is exactly a static object. It doesn't move. Everything is exactly in its stable state from the perspective of those 4 rules. Applying those 4 rules doesn't change anything about the picture. Same thing for the loaf and the boat and the tub. The more interesting ones are these oscillators. So these oscillators have multiple states, and they change between these states. This is similar to the logistic map when we were looking at the oscillating attractors. You might think that the game of life also has these oscillating states that swap back and forth between each other. So this is moving, so it's a little hard to do it while it's moving. But imagine just the up and down, where it's just a 3 vertically. So we have 1, 2, 3 cells that are alive in just a vertical state. And then we can go through all the cells and see what turns on and what turns off. So consider this top cell. It's on right now, but when it's just a vertical state, how many is it touching? Well, it's only touching one cell. It's touching the middle cell. So you need to be touching 2 or 3 live cells in order to stay alive, but this top cell is only touching one cell when it's in the vertical position. So when it's in the vertical position, that top cell is going to turn off in the next state. Same thing for the bottom cell. The bottom cell is only touching one live cell, so it's going to turn off. The middle cell is touching 2 cells. It's touching both the top and the bottom. So that middle cell is going to stay on in the next state. And this is exactly what you see. You see the top cell turns off, the bottom cell turns off, but the middle cell stays on. But it's not just the bottom and the top cell that turn off, but it's also these 2 side cells that turn on, because this cell, it's off when it's vertical, but in the vertical state, this cell is touching 3 live cells. So from the vertical state, this turns on, and from the vertical state, this turns on, this square over here. So the 2 cells on the side turn on, and the cell on the top and the bottom turn off. And what that results in is this little oscillator that goes from a vertical position to a horizontal position to a vertical position. It sort of oscillates around this middle cell that never turns off. And you can go ahead and do it yourself, apply those rules. You see that none of the other cells around the blinker change. So you have this oscillating just between these 2 states. The blinker is an oscillator between 2 states. We have a couple of other 2-state oscillators. The toad oscillates between these 2 states. The beacon oscillates between these 2 states. Again, remember, the block itself is stable, but if the block is touching another block, then the corner of this block is touching the 3 blocks in its block plus the corner of the next block. And that's 4, and so that makes it turn off. But when it turns off, now it's only touching 3, so it turns back on, and then turns off, and turns on, turns on, turns off. So the beacon is a 2-state oscillator. You also have these more complicated oscillating states. So the pulsar goes through 3 states before it has a state, and then goes through another state, and then another state, and then that state loops around back to the first state. So there's an intermediate state that it goes through, and has this 3-period oscillation. So it's not just a 2-period oscillator, it's a 3-period oscillator. Here at the bottom, this is the pentadecathlon, which is a 15-state oscillator. So you can watch this graphic. You can see that these blocks are going through 15 different configurations before it lands on a configuration that's identical to the first configuration. And then it goes through the loop again. Again, these 15 configurations are all just applications of those 4 game of life rules to every single square. So in some sense, this is the game of life is entirely deterministic. What happens to the squares is entirely determined by those 4 rules. There's an unambiguous way of applying those 4 rules. So the way that the system evolves over time is entirely deterministic. In some sense, it's reductive in the sense that we're applying those 4 rules to every single square, but the way that the rules apply requires that you consider not just the square, but the squares around that square. So it's not entirely reductive. But you get these really awesome patterns. The pentadecathlon is a very complicated pattern. I think there's a 32-state oscillator that someone found also. So you can get some big oscillators. You also have these spaceships. The spaceships are not oscillators because they don't stay in a position. So you can see this glider here moves in this regular way down the board, but you can see that it doesn't return. It never returns to its initial state because it's moving across the grids, the grid squares. So the glider is a stable pattern that moves across the screen. The lightweight spaceship, the middleweight spaceship, and the heavyweight spaceship are all other kinds of gliders that move across the board. Okay, so these are the different little pieces of the game of life, but let's actually play with an instance of the game of life. Let me go back into my okay, so here's a demo. This demo is linked in the slide deck, and I think it's linked on the reading list also, so you can play with it yourself. Let me get my head out of the way a little bit more here. But this is the game of life. So it's just a big grid. Hopefully you can see the grid on the video. And you can turn individual cells on or off. You can also just sort of move across the board, sort of setting up an initial condition with whatever configuration you want. And then the blue ones are on. The green ones show spaces that have been off, that have been on at some point in the past, but are not on now. So you can kind of ignore the green spaces. It's just showing sort of where the thing has traveled. And then you just run it. So I'm going to run it, and then it just starts applying the 4 rules, and it keeps applying it. And you can see we actually settle down into a stable state pretty quickly. This is a stable state. All of these things are little fixed, stable objects, or they're oscillators that are cycling between different states. You can see there's a bunch of little blinkers that are cycling around. And then there's a couple of still lifes. And that's the stable configuration. So I drew all that stuff on the map. But once you start applying the rules, it locks itself into some pattern of behavior. Let me try it again. If I put a bunch of stuff on the board, and maybe I try to like sort of get a piece of it that's a little bit more dense. Maybe make some little dense spots right here. Oops, that's better. Okay, so I'm just sort of putting stuff around, see what happens when I run this. A little bit more of activity, but it went away pretty quickly, and we settled again into a stable state. You can see that it's a stable state because there's 113 life cells. The number of life cells is not changing, even though we're going through generations. It's not changing because there's motion, but the motion is just in this oscillating pattern that keeps the total number of cells stable. Okay. It's a different configuration. You saw a little bit more of the activity, but I want to show you some of the well-known initial states of the game of life. Again, game of life is definitely deterministic. Everything that happens in the game of life is entirely determined by those 4 rules. But the game is also chaotic, and I want to give you a demonstration that the game is chaotic. I actually need to make this a little bit smaller. Here we go. Okay. So I'm going to hit run. This is a starting state called acorn, and you can see there are 1, 2, 3, 4, 5, 6, 7, 7 squares that are on in the initial start state. I'm going to hit run, and this is called acorn for Aristotelian reasons, as you will see shortly. I'm going to hit run now, and we will let this run for a little bit. You can see it's the same sort of pattern activity. You can see little oscillators and little still lifes showing up, but there's this sort of persistent sort of cauldron of activity that sort of moves around the middle of this screen, the middle of the board. Again, this is just the 4 rules of the game of life being applied over and over and over again. But it's enough. There's enough activity here to keep going. It sort of keeps running. It's going and going and going. We're going to watch it until it settles down into a stable state. Maybe this looks a little bit like bacteria in a petri dish, sort of moving around. The idea is that it's supposed to be evocative of life, of the complexity of life. Like, look at all that activity that arose from that little simple starting state. Right? We went for over 5,000 generations before it stopped. So now we're in a stable state. You can see that it's not changing. We're not changing how many squares are alive or how many squares are dead. So we've reached the stable state. This is the final configuration. Right? If you start something off in that little acorn pattern, this is the final configuration that you'll reach. I mean, it took about 5,000 generations to get here. So I want to run this same acorn one more time. So this is the exact same starting configuration. There are 1, 2, 3, 4, 5, 6, 7 starting states, starting squares that are on. And then I'm going to hit run. Remember last time it went for about 5,000 generations and ended with 633 life cells. So the first demo here is just to show you that Conway's game of life is deterministic. If we start it in the initial starting state, we're not changing the rules, we're not changing the starting state, so we should end up in the same final state. So I'm going to run it, and we'll watch it again. I mean, it's pretty. It looks like a living organism, sort of like a simple abstraction of living, or like a video game of life. Like this is like Sim Petri dish or something. But again, the fact that there's still this activity, it's still organized in ways and maintaining itself over time. Here now, 2,000 generations, and we're still going to go for another few generations. Just the amount of activity that was packed into that little acorn is evocative of life. Like the way that it moves around, the way that these little bubbles sort of grow and then die off, or like reach this sort of calcified state. Okay, so we're almost done here. running through the last little bit of energy, and then now we hit a stable state. Again, we're at 633 live cells in this final state. So this should prove to you that Conway's game of life is deterministic. Despite all of that chaotic activity, we know that the rules are being applied in a systematic way, and we're going to end up in the same final state that we did the first one. If I run it again, we'll end up in this exact same state again. Right? So nothing's going to change about the final state that we end up in. So we know that game of life is deterministic. Is it chaotic? So it's going to be chaotic. Remember, the definition of chaos is a system is chaotic if it's sensitive to initial conditions, if it's highly sensitive to initial conditions. In other words, if small changes to the initial state result in very large changes to the final state. So we know that the acorn configuration here will run for 5,000 generations and produce 633 live cells. I'm going to change this initial state very simply, a very small change. I'm just going to add one square, one dot right there. This is the square that I added. So I didn't add a bunch of squares. I didn't change the whole structure. I just added one square. This is a very small change to the initial conditions. And so you might think, well, what does this mean for how the acorn is going to grow? Is it going to grow the same size? Is it going to hit the same configuration at the end? Probably not. Is it going to go for 5,000 generations? Is it going to go for more than 5,000 generations? Is it going to go for less than 5,000 generations? You might want to pause the video here and think about what you expect this modified acorn to do. How much is it going to do like the regular acorn, or how much is it going to change its behavior with this small change to the initial state? All right, if you have your guesses, I'm going to go ahead and run this. And there you see, we went for less than 100 generations. We ended in 24 live cells into a stable state. We almost got there immediately. It was just a few iterations of the rules, and then we found a stable state and we just stayed there. This is very much unlike the acorn. Right? The acorn went on for almost 5,000 generations, went on for 633 live cells. This looks very, very different, although the starting states were very similar, and the rules being applied were very similar. Conway's game of life is a chaotic framework. It allows for building chaotic interactions for complex, chaotic, still deterministic, but chaotic interactions. Okay, so I want to end with a little bit more of this game of life demo. I want to show two quick things. Here's a video that shows more things that you can do in the game of life. It goes through the rules. We already know the rules. Oh, it has this dramatic music. Maybe I should turn on the dramatic music a little bit. So we've seen a lot of this stuff already, but just running through it again. Everything that happens in this grid is just a product of these rules. So here are two little gliders floating alongside each other. And most of the really interesting things you can build in the game of life are based around these gliders, or knowing how to get the gliders to hit each other in just the right way. So here we have two gliders bouncing off each other and these little still life blocks in such a way that every time they bounce into each other, they shoot off another glider off in this direction. So here's one set of gliders shooting off mini gliders in this direction. Here's another set of gliders shooting off mini gliders in the other direction, and they have them lined up so that they annihilate each other exactly. Here's two sets of gliders shooting off in different directions that go on forever. Okay, now with this glider mechanic, you can build much more interesting and much more complicated systems. So again, this is just the game of life, those four simple rules about overpopulation, underpopulation, and so on, about when to turn a cell on and off. Using those four rules, you can set up a configuration like this that does exactly what you see. I'm going to come back. In some ways, this is the most impressive demo here, but if we go back, so all of these little things are little glider guns shooting at other little glider guns to shoot off little glider guns in other directions, such that it all comes together to shoot off this little sequence of glider guns so that they all arrive in the center in just such a way to produce this higher order airplane, right? So this higher order glider. So this is gliders building gliders, right? Gliders building gliders building gliders, building gliders building gliders. I'll turn off the audio, sorry. Okay, let's do this one more time. Maybe I'm going to put this on slow speed, 0.5 speed. So every one of these gliders configuration is shooting out gliders in exactly the right pattern, and you can see some of that here, to leave gliders in this little middle track, shooting down towards the center, so that all the gliders meet up and annihilate each other in just the right way to produce this final glider that gets shot off at regular intervals down the side of the video. It's great that people discovered how to make this kind of thing. Like, this is an extremely high state oscillating pattern that is operating on sort of many levels of organization and complexity, but it's doing it in a very law-like and mechanical way, so that you get this regular behavior as a result. You get the equally spaced gliders getting shot out from the same position every single time. This is why this is called the game of life, because the kind of complexity inside the game of life allows for all sorts of constructions and operations. In fact, the operation that you see on screen right now is a Turing machine. We actually know that you can build a fully functioning Turing machine inside the game of life. And what this means is that the game of life is Turing complete. It means that the game of life can, in principle, compute any computable function. Any function that can be computed by any computer can be computed within the game of life with appropriately arranged little glider guns that are all set up. So this is the Turing machine. If you know anything about Turing machines, we'll talk about this later on in the semester. But here's the tape. Each one of these are different cells with data written on it, and here's the head on the tape that's reading from the tape and writing to the tape. Out in the corner over here is where the data storage is, or the memory storage is. So this is like a memory bank. And this memory bank is informing what actually goes on the Turing machine. So you can write and program this Turing machine in the same way that you program any other Turing machine to do a bunch of finite state operations on the tape as memory. And if you can run a Turing machine, then you can run anything that any other Turing machine can run. We'll talk about this a lot more later on in the semester, but the really important thing about a Turing machine is that it's a universal machine, is that one Turing machine can run the operations of any other Turing machine. If any Turing machine can perform a function, then you can build a Turing machine that can perform the same functions. And what that means is that if you can build a Turing machine in the game of life, and a Turing machine can compute any computable function, then you can compute any function entirely within the game of life. Any program that any computer can run, you can run in the game of life. Like Microsoft Word, the word processing software, it's like 1 million lines of code. It wouldn't be very convenient. It'd be very hard to write, to configure the Microsoft Word within the game of life. But in theory, you can build a computer within the game of life that performs the exact same operations that Microsoft Office does. Or Microsoft Word does. These are, right now you're seeing a lot of sort of visual tricks that you can do, these sort of space filling algorithms that fill the space with patterns. You have these sort of very complicated oscillating mechanisms going around. People spend a lot of time building really neat little mechanisms within the game of life. Let's see what else is here. Remember, you can compute any computable function. So where's the there's one demo here that they put an LED display, or not an LED display, but a dot matrix display. I think some of these are explained in the, here we go. Yeah, so here is again, this is just the game of life, it's just those 4 simple rules, but you can configure it in such a way that it'll produce a string of text as if it's a LED display, and you can have it produce arbitrary text. You can have it say anything you want. This is a calculator that they built in the game of life. You can do all sorts of really, really cool things in the game of life. Let me show you one cool thing that you can do in the game of life. I think, oops. This is John Conway. He's the guy who came up with the game of life. But this is maybe my favorite demo for the game of life. So you can compute any computable function within the game of life. Anything that any computer can do can be done within the game of life. one thing a computer can do is compute the states of the game of life. And what this means is that you can, within the game of life, build another model of the game of life that the one game of life runs. So that's what you see here. So this is an instance of the game of life. It's a grid where every cell is turning on or off on the basis of those same 4 rules. And using that grid and those rules, they're configuring the little gliders and so on to be themselves another instance of the game of life. So this is another cell on a higher order game of life. Right now that cell is on. Over here is another cell. It's also on. I think up here the cells are off. And as we zoom out, you'll see that the whole thing is another layer of the game of life. That you have the little cells that are on or off at the low level of operation, and then all those cells are configured so that at a higher order of operation, you have another instance of the game of life where these higher order cells are turning on and off, again, on the basis of the same 4 rules. Right? So this cell is touching 1, 2 live cells, so it'll stay alive, but this cell is only touching 1 live cell, so it turns off. And you'll see here in just a second, it'll turn on. Oh, I guess it's also touching this cell, so it stays on. Yeah, you have all of those lower order cells serving as the grid structure and the processing structure for determining whether these higher order cells turn on or off. You can see, so this one is touching 2 cells, so it'll stay on. This one's touching 2 cells, so it'll stay on. This one's only touching 1 cell, so it'll turn off. But this one turns on because it was touching 2 cells and so on. And so you have this higher order, you have another glider that's slowly making its way across. I have this at 0.5. That's what's going on here. You have this higher order glider moving across the screen according to the same 4 basic rules of the game of life. And this is the model that I want you to have of biological systems. That biological systems are complex because they're organized systematically at several different layers. There's organizations layered on organization on organization on organization. And each one of these organizations constructs a kind of whole at that level that's explained by the organization of the lower level parts. You can get very complicated higher order behavior from these low level parts, even when the low level parts are entirely deterministic, even when those low level parts are governed by very simple rules. Right? The game of life gives an existence proof that you can have a deterministic system that's chaotic and that allows for the emergence of higher orders of organization, higher orders of complexity. Now, obviously, biological systems are far more complex than the game of life, that the kind of rules that govern the behavior of the parts of biological systems are much more complex than what we see in these grid squares. I'm not arguing that the little creatures in the game of life are alive. I'm not arguing that the game of life is a good model for all of biology. But it's supposed to be suggestive. It's supposed to be suggestive that this framework built on simple rules and the organization of parts is enough to provide all of the kind of dynamical complexity that we see in real biological organisms. Maybe the game of life is too sparse. There's I think it's called Lumia. No, it's not Lumia. Linia. So Lenia. Is another version of Game of Life, but in this case, it's not just that cells are on or off, but there's a continuous gradation of being on or off, and there's also a continuous space for cells to interact. So it's not just a rigid grid structure, but there's this sort of continuity. So it's continuous both in states and in operations. So it's not fully on or fully off, but some cells are partly on and some cells are partly off. But otherwise, you have the same kind of combination and population rules. So this is a sort of a more complicated, continuous game of life. And maybe here you see more something that's closer to looking biological, something that's closer to looking like it has the kind of dynamics and behaviors that you'd expect from a biological organism. But again, this is just the game of life It's an extension of the game of life. It's a continuous version of the game of life with continuous states and continuous operations. But it's still deterministic. It's still chaotic in the ways that the classical game of life is. So all of this is just supposed to be suggestive of mechanical theories of life. I haven't given the knockdown